What if every single decision you've ever made, from the smallest choice to the life-altering ones, didn't just fade into memory, but actually splintered off into entirely new worlds? What if somewhere out there, another version of you took that job offer overseas, or said yes when you said no, or became the person you sometimes wonder about in quiet moments? It sounds like the stuff of science fiction, something from the pages of a comic book or a late-night movie. But what if I told you this idea isn't just fantasy? It's a legitimate scientific possibility, one that's gaining traction among physicists, cosmologists, and philosophers who are daring to ask one of the most profound questions we can ponder. Are we truly alone in this version of reality? Or is our universe just one thread in an infinite, shimmering tapestry of existence? Today, we're setting off on a journey to explore that very question, peering into a universe of possibilities where the lines between science and speculation blur in the most thrilling ways. We'll travel from the quantum realm, where particles exist in multiple states at once, to the vast cosmic landscapes predicted by inflationary theory, where countless bubble universes may be blooming beyond the edges of what we can see. We'll delve into ideas like the many worlds interpretation, which suggests that every quantum event spawns a new reality, and examine how these concepts aren't just abstract mathematical curiosities. They challenge everything we think we know about identity, destiny, and the nature of reality itself. This exploration is about more than just theory. It's about reimagining our place in the cosmos. By the end of our journey, you won't just see the night sky as a static canvas of stars. You'll see it as a dynamic, ever-evolving puzzle, rich with layers of mystery and potential. You'll understand how cutting-edge research is bringing us closer than ever to grasping whether alternate realities are not only possible but inevitable. So, if you've ever wondered about the roads not taken or felt that tug of curiosity about what lies beyond our perception, you're in the right place. Let's begin where all great questions start, with a bold idea and the courage to follow it wherever it leads. In the mid-1950s, a brilliant and somewhat unconventional young physicist named Hugh Everett III was grappling with a problem that had been troubling the greatest minds in quantum mechanics. The prevailing theory, known as the Copenhagen interpretation, stated that particles exist in a blurry state of multiple possibilities, a superposition until the moment they are observed, at which point they suddenly snap into a single, definite reality. This act of observation, this measurement, was a mysterious process that seemed to require a conscious observer, almost placing human consciousness at the center of the universe's workings. To Everett, this felt arbitrary and unsatisfying, a mathematical cop-out. He believed the laws of physics should be universal, applying equally to tiny particles and to the people measuring them, without any special magic happening during an observation. His revolutionary solution was breathtaking in its simplicity and its audacity. He proposed that the mathematics of quantum mechanics should be taken at face value, without adding any extra rules about observation or collapse. In his view, when a quantum event has multiple possible outcomes, all of those outcomes occur, but they don't happen here. Instead, the entire universe branches at that moment, splitting into multiple, equally real copies, each one containing one of the possible results. In one universe, the radioactive atom decays and Schrödinger's cat is found dead. In the new, freshly branched universe, the atom does not decay and the cat is alive and well. There is no collapse because there is no single outcome to collapse into. Every potentiality is realized in its own world. Everett called this the relative state formulation, but the world would come to know it as the many worlds interpretation of quantum mechanics. When he presented his doctoral thesis in 1957, the reaction from the old guard of physics, including the legendary Niels Bohr, was one of profound skepticism and even dismissal. The idea seemed too extravagant, too science-fictional, and it was largely ignored for more than a decade. Everett himself, disheartened by the cold reception, eventually left academia. But his idea refused to die. Throughout the 1970s and 80s, physicists like Bryce DeWitt began to champion the theory, arguing that it was actually the most straightforward and elegant solution to the paradoxes of quantum theory. It removed the need for a special, unexplained measurement process. It treated the entire universe as a single quantum system that evolves according to its own rules, endlessly branching into a vast, ever-growing tree of alternate histories and futures. What started as a dismissed PhD thesis has since blossomed into one of the most compelling and hotly debated frameworks for understanding the fundamental nature of our reality, suggesting that the universe we experience is just one page in an infinite library of existence. To truly grasp how a universe could branch into countless others, we need to dive into the bizarre and beautiful rules that govern the smallest building blocks of reality. This is the quantum realm, a place where the solid, predictable world we know dissolves into a shimmering cloud of probability. The core concept here is known as superposition. In our everyday experience, an object is in one place at one time. A book is on the table, not both on the table and on the shelf. But in the quantum world, a single particle, like an electron, doesn't have to choose. Until something forces it to declare its position, it can literally exist in a smeared-out state of multiple locations or multiple states, all at the same exact moment. A classic way to picture this is to imagine that coin spinning through the air. While it's spinning, you cannot definitively call it heads or tails. It is, in a very real sense, both and neither. It only becomes one or the other at the precise instant it lands in your palm. For a quantum particle, this landing is the act of measurement, of observation. But before that moment, its condition is not just unknown, it is fundamentally undefined. This isn't a limitation of our instruments, it's a fundamental property of nature itself. An electron isn't secretly in one spot, and we just haven't found it yet. It genuinely exists in a superposition of positions, with its probability of being found in any given place described by a mathematical wave of possibility. This strange behavior was stunningly confirmed by one of the most famous experiments in all of science, the double-slit test. When scientists fire a stream of particles, like electrons or photons, at a barrier with two narrow slits, you would expect them to form two neat bands on a detector screen behind it, much like throwing tennis balls at a wall with two holes. But that's not what happens. Instead, they form an interference pattern, a series of light and dark bands which is the unmistakable signature of a wave. It's as if each individual particle is passing through both slits at once and interfering with itself on the other side, a notion that defies all classical logic. The act of being a wave is its superposition state. The truly mind-bending part comes when you try to catch it in the act by placing a detector at one of the slits to see which way it goes. The moment you do this, the interference pattern vanishes. The particle, now observed, behaves like a proper little bullet and goes through one slit or the other. The act of measurement collapses the superposition, forcing the particle to pick a single, classical reality. This implies that at its most fundamental level, our universe is not deterministic but probabilistic. It operates not on certainties but on potentials. Countless outcomes are always in play, lurking just beneath the surface of what we perceive as a solid, single reality. The math of quantum mechanics doesn't predict a single result. It calculates the odds for every possible result. This probabilistic undercurrent is the engine that drives the many worlds interpretation. If the mathematics describes all possibilities as equally real, then perhaps they are. The collapse upon observation isn't a disappearance of possibilities, but a separation. The universe doesn't erase the other outcomes. It branches into new versions of itself to accommodate each and every one, from the path of a single electron to the fate of a cat in a box. This quantum weirdness isn't confined to tiny particles in a lab. It's the hidden scaffolding of everything we see, and its rules may very well scale up to create the infinite tapestry of the multiverse. But if the quantum world operates on this principle of branching possibilities, how does that scale up to the entire cosmos? How do we get from the behavior of a single electron to the existence of entire universes with different laws of physics? The bridge between these two astonishing ideas is a theory known as cosmic inflation, and it was first proposed in the early 1980s by a physicist named Alan Guth. He was trying to solve a few nagging problems with the standard Big Bang model. For instance, why does the universe appear so incredibly uniform in every direction we look? The cosmic microwave background radiation, that faint afterglow of the birth of the universe, has almost exactly the same temperature whether we look east, west, north, or south. This presented a real puzzle because according to the original Big Bang timeline, these distant regions of space would never have had enough time to exchange heat and reach a common temperature. They were simply too far apart, separated by a distance that light could not have crossed in the age of the universe. Guth's brilliant solution was to propose that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, inflating in size by a factor of at least 10 to the 26 in a tiny sliver of time. This incredible burst of growth, far faster than the speed of light, stretched a microscopic, homogeneous patch of space into the vast, observable cosmos we see today, neatly explaining its uniformity. But the most fascinating implication of inflation wasn't its solution to these initial problems. It was a consequence that Guth himself hadn't initially anticipated. The mechanism that drives inflation is a peculiar type of energy field, often called the inflaton field. The theory suggests that while this field causes most of space to inflate rapidly, it can also undergo quantum fluctuations, tiny, random jumps in its energy value at the subatomic level. Here is where the quantum world and the cosmic world perform a breathtaking duet. Those tiny quantum jitters, those random fluctuations born from the uncertainty principle, don't get smoothed out. Instead, the violent expansion of inflation stretches them from subatomic size to astronomical proportions, imprinting them onto the fabric of spacetime itself. These imprints eventually became the seeds for all the large-scale structure in our universe, the vast cosmic web of galaxies and galaxy clusters we observe today. But the story doesn't end there. For inflation to stop in our region of space, the inflaton field had to decay, releasing its energy to form the hot soup of particles of the conventional Big Bang. However, the mathematics of the theory suggests that this decay might not happen everywhere at once. In fact, for the process to start, it may be that inflation is eternal. While it ends in one region, creating a single, bubble universe like our own, the overall inflationary space continues to expand at an incredible rate. New regions are constantly popping into existence and inflating, and within those regions, quantum fluctuations can cause some patches to decay into new bubble universes, while the space between them continues to inflate forever. This is the breathtaking vision of the inflationary multiverse, Our entire observable universe, with its hundreds of billions of galaxies stretching out over tens of billions of light years, is just a single bubble in a vast, ever-growing cosmic foam. Each of these bubbles is a separate universe, potentially with its own unique set of physical constants and laws. In our bubble, the strength of gravity, the mass of an electron, and the other fundamental forces are fixed to values that allow for atoms, stars, planets, and life to form. But in another bubble, the constants might be radically different. Perhaps in one, gravity is so strong that the entire universe collapses back in on itself in an instant. In another, the nuclear forces are too weak to ever bind protons and neutrons together, meaning no atoms ever form, and the universe is just a cold, thin haze of elementary particles. This concept offers a powerful explanation for the apparent fine-tuning of our universe. It's not that our universe was magically designed for life. It's that in an infinite ocean of possibilities, a vast number of universes are sterile and empty, but we inevitably find ourselves in one of the rare bubbles where the numbers just happen to come out right. This brings us to one of the most intriguing and controversial ideas at the intersection of quantum physics and philosophy: the role of the observer. We've seen how measurement forces a quantum system to choose a state, but what exactly constitutes a measurement? Is it the physical interaction of a detector? Or does it require something more, a conscious mind to register the result? This question lies at the heart of the observer effect, and it pushes us into a realm where science grapples with the very nature of awareness and existence. Some interpretations of quantum mechanics, most notably the one put forward by the brilliant mathematician John von Neumann, suggest that consciousness itself is the ultimate catalyst that collapses the wave function. In this view, all the machinery of the universe, the particles, the fields, the detectors, can be described by the same quantum equations, all existing in a blur of superposition. The chain of cause and effect can be traced from a particle to a Geiger counter to a computer screen, with each step still enmeshed in a quantum haze of possibilities. According to this perspective, the collapse doesn't happen until the information from that computer screen finally enters the subjective experience of a conscious observer. It is the act of knowing, of becoming aware of an outcome, that finally pins down a single, concrete reality from the soup of potentialities. This is a staggering proposition. It implies that mind and universe are not separate. They are deeply, fundamentally intertwined. Reality, in a very literal sense, might not be fully realized until it is perceived. To illustrate just how puzzling this interface can be, consider the thought experiment known as Wigner's friend, devised by physicist Eugene Wigner. Imagine his friend is inside a sealed lab, about to perform the classic Schrödinger's cat experiment. He prepares the apparatus and he observes the result. From the friend's perspective inside the lab, the wave function has collapsed. He now knows with certainty whether the cat is alive or dead. But now, Wigner himself is outside the closed laboratory door. From his perspective, the entire lab, including his friend, the cat, and the equipment, is still a single, isolated quantum system. As far as Wigner's equations are concerned, his friend is in a superposition of having seen a live cat and having seen a dead cat. So, who is right? When does the actual collapse occur? Is it when the friend looks, or only when Wigner opens the door and his friend tells him the result? This paradox highlights the bizarre difficulty of locating the precise moment a probability becomes a fact, and it suggests that consciousness might not be a mere passenger in the universe, but perhaps an active participant in its creation. This leads to a profound and deeply personal question about our own daily lives. If consciousness plays such a fundamental role, then what does that mean for the choices we make? Every day, we are all conscious observers, constantly making measurements of the world around us. You choose to look at your phone, you decide what to have for lunch, you observe the outcome of a conversation. If the many worlds interpretation is correct, each of these conscious observations could be a branching point. Your awareness isn't just passively recording a predetermined timeline. It might be actively navigating an infinite labyrinth of possibilities. Its focus selecting one path forward while other versions of your consciousness simultaneously experience all the other paths you could have taken. This transforms the concept of free will into something even more complex. It's not just about choosing your future in one universe. It's about the fact that your process of choosing may be what creates the splintered realities in the first place, with every version of you believing just as firmly that their path was the one that was chosen. So if every conscious observation can branch reality, then the implications for our own daily existence are nothing short of revolutionary. Think about the sheer volume of choices you make in a single day, from the mundane to the monumental. You hit the snooze button one more time, you choose coffee over tea, you take a different route to work to avoid traffic, you decide to speak up in a meeting or bite your tongue. Each of these moments in the many worlds view is not a solitary event confined to our timeline. They are each a fork in the road, a point where the universe you inhabit diverges from another, creating a new, parallel world where a slightly different version of you made the opposite choice. This branching isn't just for the big, life-altering decisions like accepting a marriage proposal or moving to a new country. It happens for the tiniest quantum events that percolate up to our macroscopic scale. The exact neural pathway that fires in your brain when you're deciding what to make for dinner represents a quantum event. In one universe, that particular sequence of neural firings leads you to order a pizza. In the brand new universe that just split off, a different, random quantum fluctuation influenced your neurons, and you decided to cook a stir-fry instead. Both versions of you feel you made a conscious, free choice, and both are correct within their own now separate realities. This is the mathematical mechanism of quantum decoherence at work. It's the process that takes all those shimmering probabilities and makes them seem definite to us, not by collapsing them, but by allowing the different possibilities to stop interacting with each other, effectively creating independent worlds. So that artist you dreamt of becoming, they exist. The scientist, the world traveler, the person who stayed in their hometown, they are all out there, living the lives defined by the choices their version of you made at every single branching point. This perspective can be incredibly liberating when we think about our own past. Feelings of regret or nostalgia, that wistful wondering about the road not taken, take on a completely new character. You didn't actually miss out on that other path. Some other version of you is living it right now, experiencing the joys and challenges of that alternate life. Your regret can transform into a sense of cosmic curiosity. It allows you to reframe your own life's narrative not as a single, fragile thread that could have easily snapped, but as one robust strand in an infinite tapestry where every potentiality is woven into the grand design. It suggests that there is no one correct path your life was meant to take. All versions are equally valid and equally real. This doesn't devalue our experiences. If anything, it makes our current journey feel more precious, knowing it is uniquely ours among the infinite possibilities, while simultaneously freeing us from the weight of believing we made a single, catastrophic mistake that ruined our one shot at happiness. This framework also turns our traditional notions of free will and destiny inside out. If every possible choice is made in some universe, then in a sense, you have the ultimate free will. Every option is selected. But from the perspective of the individual version of you experiencing this timeline, it feels like you are exercising a singular free will to make this specific choice. The you in this universe cannot will yourself into the universe where you made a different decision. Your consciousness is tethered to this specific branch. So we still experience the profound feeling of making choices, of steering our own ship, even though the ocean we are sailing is unimaginably vast and contains every possible course. It's a beautiful paradox. We have both complete free will and no free will at all, depending on whether you view the cosmos from the perspective of the single observer or the grand, branching multiverse. This challenges the very idea of a predetermined destiny, replacing it with a spectrum of destinies, each one actualized and being lived to its fullest. And if every choice we make in our personal lives can branch into new realities, then what about the colossal, world-altering events that define our collective history? These are the moments that echo through centuries, the hinges upon which the door of human experience swings. We often play the game of what if, wondering how different our world might be if a single battle had gone the other way, if a pivotal invention had never been made, or if a great leader had lived longer. In the framework of the multiverse, these aren't just idle speculations or fascinating thought experiments. They are actual, tangible realities playing out in countless other worlds. The physicist Max Tegmark offers a compelling way to think about this. If an event has a probability greater than zero, no matter how infinitesimally small, then in a sufficiently vast or infinite multiverse, it is not just possible, it is guaranteed to happen somewhere. This mathematical certainty transforms our entire conception of history from a single, linear narrative into a sprawling, dynamic mosaic where every conceivable possibility finds its place. Consider one of the most popular historical pivots, the extinction of the dinosaurs 66 million years ago. In our timeline, a massive asteroid struck the Earth near what is now the Yucatan Peninsula, triggering a catastrophic winter that wiped out nearly 3/4 of all species and cleared the ecological stage for mammals to eventually rise to dominance. But what if that asteroid had missed? What if it had arrived a few minutes earlier or later, striking the deep Atlantic or Pacific Ocean with less devastating effect? In those alternate universes, the reign of the dinosaurs likely would have continued. Without that mass extinction event, small, shrew-like mammals might have remained forever scurrying in the undergrowth, never evolving the traits that would eventually lead to primates, hominids, and us. The entire evolutionary trajectory of complex intelligence might have been entirely different. Perhaps a species of highly evolved, intelligent dinosaur, a dinosauroid, would have developed tool use, language, and civilization, looking up at the stars and wondering about their own place in the cosmos, completely unaware that in another reality, their lineage was cut short by a random rock from space. Zooming forward to more recent human history, the Battle of Waterloo in 1815 stands as another classic branching point. In our world, the forces of the Duke of Wellington, combined with the crucial late arrival of the Prussian army, defeated Napoleon Bonaparte, ending his ambitions for a French-dominated Europe and setting the continent on a path toward a new balance of power. But imagine a universe where a sudden, torrential downpour the night before did not turn the battlefield into a muddy quagmire, allowing Napoleon to launch his artillery attack earlier and with greater effect. Or a world where the Prussian forces were delayed by a collapsed bridge. In that reality, Napoleon might have secured a decisive victory, potentially preserving his empire, altering the map of Europe for generations, and dramatically changing the cultural and political forces that led to the First and Second World Wars. The entire 19th and 20th centuries would have unfolded under a completely different set of alliances, ideologies, and national boundaries. The French language might be the dominant global tongue of diplomacy. The United States might have remained more isolationist without a European war to draw it in, and the very concept of democracy might have taken a different form. These alternate histories aren't confined to military turning points. They extend to scientific and cultural revolutions as well. What if the Library of Alexandria had never burned, preserving a vast treasury of ancient knowledge that could have accelerated the scientific revolution by over 1,000 years? What if Nikola Tesla had secured the funding to complete his Wardenclyffe Tower, potentially giving us wireless global energy transmission a century ago and revolutionizing our relationship with technology and the environment? What if a different artist had been commissioned to paint a ceiling in Rome, and the world never received the transcendent genius of Michelangelo's Sistine Chapel? In a multiverse, these aren't losses to be mourned, they are realities being enjoyed. Somewhere, scholars are studying texts from Alexandria that we can only dream of. Somewhere, cities are powered by clean, wireless energy beamed from towers. Somewhere, tourists are gazing up at a different masterpiece, just as awe-inspiring in its own way. This perspective does more than just fuel our imagination. It profoundly influences our understanding of causality and progress. Our traditional view of history is often teleological. We see the past as a straight line leading inevitably to our present, a narrative of cause and effect where one thing clearly leads to another. But the multiverse view shatters this linearity. It suggests that progress isn't a predetermined march but a meandering path through a garden of forking ways. An event we see as a triumphant victory in our timeline could be a tragic defeat in another, and neither is more correct than the other. It challenges the great man theory of history, which attributes change to the actions of a few powerful individuals. While individuals certainly matter, the multiverse concept shows that their impact is contingent on a million tiny, random quantum events that could easily have gone another way. It introduces a powerful sense of humility, reminding us that our current reality is not the pinnacle of an inevitable journey, but simply one possible outcome among an infinity of others, each with its own triumphs, tragedies, and wonders. This realization encourages us to see our own time not as the final product of history, but as a moment of flux, one branch among countless others, still ripe with possibility and change. But if these other universes are forever beyond our reach, separated by unimaginable distances or different dimensions, how could we ever hope to find evidence for them? This is the monumental challenge facing cosmologists today. How do you test the untestable? How do you prove the existence of something that, by its very definition, might exist outside our observable reality? The answer lies not in direct observation, but in the subtle art of looking for cosmic fingerprints, anomalies, echoes, and shadows in the data we can collect that point toward a reality far grander than our own. One of the most promising hunting grounds for these fingerprints is the cosmic microwave background, that ancient afterglow of the Big Bang that paints the entire sky. This faint radiation is a snapshot of the universe when it was just 380,000 years old, and it is incredibly uniform, but not perfectly uniform. Tiny fluctuations in temperature, variations of a mere millionth of a degree, reveal the seeds of all future structure. According to the theory of eternal inflation, our universe is one bubble in a frothing cosmic sea. And just like bubbles in a sink, they might occasionally collide. If a neighboring bubble universe had bumped into ours in the distant past during its early inflationary phase, that collision would have sent a ripple through the fabric of space-time. That ripple would have left an indelible and potentially detectable imprint on the CMB, a distinct circular pattern of temperature variations. teams of scientists have meticulously scoured the data from satellites like Planck, searching the entire sky for these telltale bullseyes. While a few intriguing candidates have been identified, none have yet risen to the level of definitive proof. The search continues, becoming ever more precise, as this represents one of the most direct ways our universe might literally bear the scars of a close encounter with another. Beyond looking for bruises from cosmic collisions, physicists are also turning to the most powerful machine ever built by humanity, the Large Hadron Collider. This 27-kilometer underground ring smashes protons together at nearly the speed of light, recreating conditions not seen since the first fraction of a second after the Big Bang. One of the original hopes was that these incredible energies might produce direct evidence of extra dimensions, a key prediction of string theory that would provide a plausible mechanism for a multiverse. The idea is that gravity may be so weak in our world because it is actually spread out or leaking into these other spatial dimensions. While the LHC has yet to find any direct evidence of these extra dimensions, it continues to probe the extreme frontiers of energy, and every new discovery about the fundamental particles and forces refines our understanding of what is possible, constraining the vast landscape of potential multiverse theories. Perhaps the most intriguing experimental approaches are happening not at cosmic scales or in massive colliders, but on quiet laboratory tables. Quantum physicists are designing increasingly sophisticated experiments to test the very foundations of the many worlds interpretation. The principle of decoherence is key here. It's the process that explains why we don't see everyday objects in superposition, why a cat is never observed to be both dead and alive. By meticulously controlling tiny objects like small strips of metal or clouds of atoms, cooling them to near absolute zero to isolate them from their environment, scientists can actually observe these objects enter a quantum superposition and then watch as decoherence makes the different branches effectively independent. While this doesn't prove those other branches become full-fledged universes, it demonstrates the physical mechanism that would allow for that branching to occur. It shows that the quantum weirdness isn't confined to tiny particles but can be scaled up, bringing the bizarre reality of quantum possibilities one step closer to our human-scale experience. These experiments are pushing the boundary between the quantum and classical worlds, and with each advance, they provide more compelling, tangible evidence for the processes that could underpin a multiverse. All of this work, from staring at the ancient sky to smashing particles and manipulating atoms, represents a profound shift in scientific thought. We are moving from metaphysical speculation to empirical investigation. The goal is to find a signature, a prediction that only a multiverse model can explain, that would be exceedingly difficult to account for in a single universe theory. It's a painstaking process of connecting the deepest theoretical ideas to measurable phenomena. While a smoking gun remains elusive, the very fact that these ideas are being pursued with such rigor and creativity shows that the concept of multiple realities is no longer confined to the pages of philosophy books or science fiction. It is a legitimate and increasingly central part of the scientific conversation about the ultimate nature of existence. And if even one of these searches proves successful, it would irrevocably alter our understanding of reality, forcing us to ask not just what exists in our universe, but what could possibly exist in the infinite array of worlds beyond. So if an infinite number of bubble universes are constantly blooming into existence, each with its own random set of physical laws and constants, we are immediately faced with a profound and beautiful puzzle. Why does our particular universe seem so perfectly, exquisitely calibrated for our existence? The strength of gravity, the precise charge of an electron, the exact energy levels that allow carbon atoms to form in the hearts of stars, tweak any of these fundamental numbers by even a tiny fraction, and the entire cosmic edifice that supports life would come crashing down. If gravity were slightly stronger, the universe would have collapsed back on itself in a fiery big crunch almost immediately after the Big Bang, never giving stars or planets a chance to form. If the nuclear strong force were just a bit weaker, protons wouldn't stick together, meaning no atomic nuclei, no chemistry, and just a boring soup of hydrogen atoms forever. This apparent fine-tuning has long been used as an argument for a divine creator, a universe deliberately designed with us in mind. But within the framework of the multiverse, there is a far more natural, and in some ways even more humbling, explanation. It's known as the Anthropic Principle. The word anthropic comes from the Greek word for human, but the principle isn't about humans specifically, it's about observers in general. In its simplest form, it states that we should not be surprised to find ourselves living in a universe that has the right conditions for life, because we could not possibly find ourselves in one that doesn't. It is a straightforward selection effect. Imagine a group of intelligent fish having a philosophical discussion deep in the ocean. One of them might remark, "Isn't it astonishing how perfectly adapted our world is for us?" The pressure is exactly right for our bodies, the salinity of the water is ideal for our gills, and the temperature is perfectly suited to our biology. It must have been made just for us. What the fish fails to realize is that they are having this conversation in the one environment in the vast, diverse ocean that can support their particular form of life. They are not considering the countless other parts of the ocean, the freezing abyssal plains, the scalding hydrothermal vents, the barren, sunlit surface, that are utterly hostile to them. Their observation is correct, but their conclusion is backwards. The environment wasn't designed for them. They evolved to survive within the narrow constraints of the environment they inhabit. We are those fish, but on a cosmic scale. In the infinite foam of the inflationary multiverse, there will be countless bubbles where the constants are wrong. Universes where gravity is too strong, or electromagnetism is too weak, or the cosmological constant is so large that space-time rips itself apart in a violent big rip. These universes are stillborn, dark, and empty, devoid of any structure complex enough to ever wonder about its own existence. But there will also be a tiny, tiny fraction of universes where, by pure random chance, the numbers fell within the incredibly narrow Goldilocks zone that permits atoms, stars, planets, and ultimately, life. And in those universes, observers will eventually evolve, look around, and marvel at how perfectly tailored their world seems to be. The fine-tuning isn't a puzzle to be solved. It's a necessary precondition for us to be here to notice it in the first place. This perspective doesn't make our universe any less special, but it recontextualizes that specialness. We are not the preordained purpose of creation. We are the lucky winners of the ultimate cosmic lottery, living in one of the rare, shimmering bubbles where the laws of physics allowed a story to be written. This realization has profound implications for our place in the cosmos. It instills a sense of both profound humility and incredible rarity. We are not at the center of the universe, but we are inhabitants of a remarkably privileged corner of the multiverse. It also shifts the goal of fundamental physics. Instead of asking, why do the constants have these specific, life-giving values, we can now ask, what is the mechanism that generates the variety of constants across the multiverse, and how do we calculate the probability of a universe like ours appearing? This is a question that theories like string theory, with its vast landscape of possible vacuum states, are desperately trying to answer. The Anthropic Principle provides a powerful framework for explaining the world we see, but it also challenges us to dig even deeper into the mathematical bedrock of reality to understand the rules of the lottery itself. And as we accept that life can only emerge in universes with the right rules, our minds naturally stretch to contemplate what form that life might take, not just here, but everywhere the numbers allow. And if our universe is just one of countless others, each with its own unique set of physical laws, then the very definition of life itself must expand beyond anything we can currently conceive. Here on Earth, we are carbon-based life forms dependent on liquid water and a specific range of temperatures, existing in 3 dimensions of space and 1 of time. But this is merely one solution to the problem of existence, a single recipe that worked in our particular cosmic kitchen. In the grand multiverse, the menu of life is likely infinitely more diverse and bizarre. The field of exobiology, which speculates about life on other planets, already pushes the boundaries of our imagination, but it is still fundamentally constrained by the constants of our own universe. When we truly embrace the multiverse, we must let go of even those anchors and consider biospheres built from entirely different blueprints, operating under rules that would seem like pure magic to us. Consider the element silicon, often proposed as a potential alternative to carbon. It sits directly below carbon on the periodic table, meaning it shares some similar chemical properties, specifically the ability to form 4 bonds with other atoms, the foundational talent for building complex molecules. On a world with a different atmospheric composition and temperature range, silicon-based life might not be a far-fetched idea. Imagine a planet where the surface is so hot that water would instantly boil away, but where pools of liquid sulfur or methane exist. In such a place, silicon could form complex chains and structures, perhaps creating creatures with crystalline skeletons and metabolisms based on silane compounds instead of the carbon-based compounds we know. Their biology would be utterly alien, potentially slow-moving and mineral-like, perceiving the world through senses we cannot begin to imagine, perhaps detecting subtle shifts in magnetic fields or sensing the planet's seismic vibrations directly. But why stop at the periodic table? In a universe where the strength of electromagnetism is stronger, atomic nuclei might hold together more tightly, allowing for entirely new, stable elements that don't exist in our reality. Life in such a place could be based on an element we have no name for, forming biological structures of unimaginable durability and complexity, or contemplate a reality where gravity is significantly weaker. On a large, low-density planet, immense, fragile beings could evolve, towering like living clouds or vast, gossamer sheets that float through a thick atmosphere, their forms so delicate they would collapse under their own weight in our world. Conversely, in a high-gravity universe, life might be squat, incredibly dense and powerful, moving with a deliberate, slow force, its circulatory system a high-pressure marvel of engineering. Then we have the truly exotic possibilities that strain the limits of our language. What does life look like in a universe with more than 3 spatial dimensions? We are 3-dimensional beings who can perceive the 2-dimensional shadow of a 3-dimensional object, but we cannot truly visualize a 4th spatial dimension. A creature that naturally existed in 4 dimensions would perceive our entire world in a way we cannot comprehend. It could see inside every closed container, behind every wall, and inside every living thing simultaneously. To such a being, we would appear flat and enclosed like characters on a page. Their biology wouldn't be based on cells and organs as we understand them, but on hyper-dimensional structures and processes. Communication with such an entity might be impossible, not just because of language, but because the very framework of our perception and existence is fundamentally different. And what of the ancient sci-fi trope of beings of pure energy? In a universe where the forces are configured differently, stable structures of energy might be possible conscious, self-aware patterns of light or plasma, dancing within the magnetic fields of a star or flowing like rivers through the emptiness of space. These entities wouldn't have a lifespan as we know it. They might be near immortal, thinking thoughts that span millennia, communicating through modulated radiation bursts, and perceiving time as a fluid dimension they can navigate. Their entire existence would be a form of physics we can only describe with advanced mathematics, a symphony of forces playing out on a cosmic scale. This expansion of possibility is not just an intellectual exercise, it serves a crucial purpose. It ruthlessly dismantles our Earth-centric, carbon-chauvinist view of biology. It forces us to admit that life is not a phenomenon specific to our planet's conditions, but a potential outcome of physics itself, wherever the constants allow for complexity, information processing, and evolution to occur. The conditions we consider extreme, the crushing pressures of a gas giant's interior, the vacuum of space, the searing heat near a hydrothermal vent, are merely extremes from our parochial viewpoint. In the infinite multiverse, every environment is someone's home. A world that is a frozen, airless wasteland to us could be a temperate, thriving ecosystem to a life form that metabolizes solid nitrogen and breathes argon. This realization is the ultimate lesson in cosmic humility, reminding us that we are not the standard for the universe, but a single, fascinating data point in a vast and varied cosmic experiment. This idea that our every action might ripple outward, spawning entire new realities where every possible consequence is realized, forces us to confront one of the most challenging philosophical questions imaginable. What does it mean to be a moral agent in a multiverse? If a version of me in another timeline is already experiencing the positive outcome of the good deed I chose not to do, and another version is suffering the consequences of the harmful action I decided against, does that somehow dilute my own sense of responsibility right here in this universe? It's a question that splits thinkers into two very distinct camps, each with profound implications for how we live our lives. On one side, there's a risk of what we might call multiverse-induced moral complacency. This is the notion that if every possible action is taken by some version of yourself somewhere, then the specific choices you make in this timeline begin to feel less significant. Why agonize over a difficult ethical decision if, in a branch universe just a fraction of a Planck length away, another you made the opposite choice and is dealing with the fallout? This perspective could be used to rationalize a kind of cosmic nihilism, a shrugging off of personal accountability because in the grand, infinite scheme of things, all outcomes are guaranteed to occur. It potentially undermines the very foundation of ethical living, which is the understanding that our choices matter because they have real, singular consequences for ourselves and others. If those consequences are no longer singular but are instead spread across an infinity of selves, the emotional and moral weight we attach to our decisions could, in theory, evaporate. But there exists a far more compelling and, I would argue, more beautiful counterargument. Rather than leading to apathy, the multiverse perspective could actually be the ultimate catalyst for a deeper, more radical form of empathy. Think about it. If the many worlds interpretation is correct, then it isn't just your positive choices that are being actualized elsewhere. It is also every moment of pain, suffering, and regret experienced by versions of you who made worse decisions. Somewhere, a version of you is living with the devastating guilt of a cruel word spoken in anger that you, in this timeline, managed to hold back. Somewhere, a version of you is dealing with the financial ruin of a reckless gamble that you wisely avoided. This isn't an abstract concept, it's a staggering thought experiment in shared identity. While these other versions are physically separate, the idea that they are still, in some fundamental quantum sense, you, can foster an incredible sense of connection and compassion for all the possible paths a life can take. It challenges you to make the best possible choices, not just for the benefit of your immediate world, but out of a sense of kinship and responsibility for the well-being of all your other selves navigating their own challenging realities. Your good deed in this universe isn't rendered meaningless. It becomes a vital act of grace for the one version of you that gets to experience its positive outcome. This leads us directly into a deep philosophical debate about the nature of identity itself. What does it mean to be you across multiple universes? Are these other versions truly you, or are they merely distant cousins who shared a common origin point? If they are not conscious of your experiences and you are not conscious of theirs, can they be said to share your moral worth? This gets to the heart of what philosophers call personhood. If we consider a person to be a continuous stream of conscious experience, then each branched version is indeed a separate individual from the moment of the split onward. They have their own first-person perspective, their own memories, their own joys and sorrows. From this viewpoint, the ethical imperative shifts. We are not responsible for these other selves, but we are responsible to the principle that all conscious experiences have value. The knowledge that your action will create a universe where suffering occurs should carry moral weight, even if you yourself will never experience that suffering. It becomes a cosmic extension of the golden rule. Make choices that you would wish all your alternate selves to make, thereby minimizing suffering and maximizing flourishing across the entire branching tree of existence. Ultimately, the multiverse doesn't let us off the ethical hook. It expands the scope of our moral consideration from the parochial to the panoramic. It demands that we think not only globally about the impact of our actions on other people and our planet, but cosmically about the very real possibility that our decisions echo across the fabric of reality, actualizing worlds of beauty or worlds of despair. This isn't about guilt, it's about mindful agency. It invites us to live with greater intention, compassion, and wisdom, understanding that while we may only directly experience one timeline, our choices participate in the creation of them all. This profound expansion of ethical thought perfectly prepares us for the next step in our journey, where we move from theory to simulation, exploring how technology is beginning to allow us to create and experience alternate realities for ourselves. While the multiverse presents a vision of reality branching endlessly according to the laws of physics, we are not content to be mere passengers on this cosmic journey. We possess a deep, innate drive to actively explore these possibilities, to craft our own alternate experiences, and we are rapidly developing the technology to do just that. This brings us to the fascinating realm of virtual and simulated realities, where the lines between the world we inhabit and the worlds we imagine are beginning to blur in the most extraordinary ways. Today's virtual reality technology offers a tantalizing glimpse into this future. With a headset and motion controllers, you can be transported to a meticulously rendered digital landscape, whether it's the surface of Mars, the depths of the ocean, or a fantasy realm of pure invention. Your brain, receiving coordinated sensory input from your eyes and ears, largely accepts this digital environment as your reality for the duration of the experience. You can look down and see a virtual body that moves when you move, reach out with virtual hands to manipulate digital objects, and feel a genuine sense of presence and immersion. This is more than just advanced entertainment. It is a form of practical, experiential philosophy. It allows us to literally step into a what-if scenario, to live for a moment in a world operating under a completely different set of rules, and in doing so, it forces us to question the very nature of our own perception. What defines reality if a convincing facsimile can be generated by a computer and a pair of screens? This line of questioning leads us to one of the most provocative ideas in modern thought, the simulation hypothesis. Popularized by philosopher Nick Bostrom, this argument suggests a startling possibility. If it is conceivable that a future civilization could develop computing power vast enough to run incredibly detailed simulations of conscious beings, perhaps even simulations of their own ancestors, then the number of simulated minds could eventually far exceed the number of biological original minds. From a statistical standpoint, if that future ever arrives, the odds that we are living in that original, base reality, rather than in one of the myriad simulations, become astronomically low. In essence, Bostrom's trilemma posits that at least one of three propositions must be true: that almost all civilizations at our level go extinct before becoming technologically mature, that almost no technologically mature civilizations are interested in running such simulations, or that we are almost certainly living in a computer simulation. This idea, while deeply speculative, creates a powerful bridge between the physical multiverse and a digital one. It proposes that alternate realities might not require inflationary bubbles or quantum branching. They could simply be software running on some unfathomably powerful computer, perhaps even nested within simulations within simulations. It suggests that the fundamental stuff of reality might not be matter or energy, but information, that the universe is, at its core, computational. This technological and philosophical pursuit reveals something profound about our species. Our desire to create and explore virtual worlds is not a new fad. It is a modern extension of an ancient human impulse. For millennia, we have used stories, art, and theater to transport ourselves to other places and lives. We have always hungered to see through another's eyes, to experience things beyond the limitations of our physical circumstances. Virtual reality and the concept of the simulation are simply the latest and most powerful tools in this timeless endeavor. They represent the culmination of our quest to not just imagine alternative realities, but to inhabit them, even if only temporarily. This drive is a testament to our boundless curiosity and our refusal to be confined to a single, predetermined experience of existence. As we push the boundaries of what is possible with technology, we are essentially building external manifestations of the multiverse concept, creating pocket dimensions where we can experiment with identity, physics, and narrative, fulfilling that deep-seated need to peer into the universe of possibilities that has captivated us from the very beginning. Long before physicists like Hugh Everett were sketching out equations for branching universes, storytellers and artists were mapping these territories with the tools of metaphor and imagination. This human fascination with roads not taken and selves unmade has found a profound home in our culture, from the pages of literature to the spectacle of blockbuster cinema. One of the earliest and most elegant explorations comes from the Argentine writer Jorge Luis Borges in his 1941 short story, The Garden of Forking Paths. He describes a labyrinthine novel that is itself a metaphor for time, a book where all possible outcomes of every event occur simultaneously, each one branching off into a new future. In Borges' vision, time is not a single, linear thread but a sprawling, infinite network where all possibilities coexist, a concept that chillingly prefigures the many worlds interpretation of quantum mechanics by over a decade, proving that the artistic mind can sometimes arrive at scientific truths through intuition and narrative alone. This theme of forking paths exploded in popularity throughout the 20th century, becoming a staple of science fiction and fantasy. Philip K. Dick's novels, such as The Man in the High Castle, plunged readers into a world where the Axis powers won World War II, using the alternate history not just as a setting but as a lens to examine our own reality's fragile sense of normalcy and truth. These stories do more than entertain, they act as philosophical playgrounds. They allow us to safely experiment with questions of identity and destiny. If a version of you in another world is a hero and you are a coward, which one is the real you? These narratives challenge the very core of our self-perception, suggesting that identity might be more fluid and contextual than we ever dared to believe. In recent years, perhaps no entity has done more to bring the concept of the multiverse into the global mainstream than Marvel Studios. Films like Doctor Strange in the Multiverse of Madness and the storyline of the Loki series have turned quantum branching from an abstract idea into a vibrant visual spectacle. We see characters literally bumping into their variants, worlds where everyone is a cartoon dinosaur, and entire realities governed by different physical laws. While these depictions are sensationalized for entertainment, they serve a crucial purpose. They provide a shared cultural vocabulary for these incredibly complex scientific ideas. Millions of people who might never open a physics textbook are now familiar with terms like nexus event and branch timeline because a superhero movie made them exciting and accessible. This pop culture adoption demystifies the science and fuels public curiosity, often inspiring young viewers to seek out the real physics behind the fantasy. The conversation between art and science is never a one-way street. Just as science inspires new worlds for storytellers, compelling fiction can actually influence the direction of scientific inquiry. A powerful narrative can capture the imagination of a young student who later becomes a physicist, determined to find the real-world evidence for the wonders they read about in books. These cultural artifacts also shape public perception, making society more receptive to radical scientific ideas. When a theory like the multiverse is presented, it doesn't arrive in a vacuum. An audience already softened by years of exposure through film and literature is more likely to be open-minded than dismissive. This creates a fertile ground for scientific advancement, where the public is an engaged participant in the conversation, not just a passive recipient of facts. The shared stories we tell about alternate realities become a bridge, connecting the abstract mathematics of cosmology to the deeply human questions of choice, chance, and who we might have been. It's a common and comforting assumption that the mind-bending concept of a multiverse is a purely modern invention, a product of 20th century quantum mechanics and cosmic inflation. But the truth is far more fascinating. The human imagination has been dancing with the idea of multiple worlds for millennia, long before we had the mathematical language to describe it. This profound curiosity appears to be a universal thread woven through the tapestry of human thought, emerging independently in cultures separated by vast oceans and centuries. By tracing this lineage, we see that our current scientific theories are not a radical break from the past, but rather the latest chapter in an ancient and enduring story. In the West, we can journey all the way back to the 5th century before the Common Era, to the Greek philosopher Democritus. Along with his teacher Leucippus, Democritus pioneered the atomic theory of the universe. He proposed that everything in existence is composed of tiny, indivisible, and eternal particles called atomos, meaning uncuttable, moving through an infinite void. But his vision didn't stop there. From this foundation, Democritus and his followers, known as the atomists, made a breathtaking leap. They reasoned that if the void is truly infinite and the number of atoms is limitless, then the combinations and collisions of these atoms must be happening everywhere, not just here. They concluded that there must be an infinite number of worlds coming into being and passing away throughout this boundless emptiness. Some of these worlds, they suggested, would be devoid of life and water, while others might be teeming with it. Some could even have suns and moons different from our own. This was a philosophical multiverse, born not from wave functions but from pure, elegant reasoning about the nature of matter and space. It was a stunningly prescient idea that laid a conceptual groundwork which would lie dormant for over 2,000 years, waiting for science to catch up. Meanwhile, on the other side of the world, Eastern philosophical and religious traditions were developing intricate cosmologies that also embraced multiplicity, though through a very different lens. In Hinduism, the concept of countless universes is deeply embedded in its sacred texts. The Puranas, for instance, describe a vast, cyclical model of creation and destruction. Our universe, or Brahmanda, the cosmic egg, is just one of many that emanate from the body of the divine. These universes are often depicted as being like bubbles in a foam or seeds on a vine, each with its own timeline and characteristics, all existing within an endless divine reality. This is not a cold, mechanical multiverse, but a living, breathing, spiritual one, where the act of creation is an ongoing, dynamic process. Buddhism offers another profound parallel with its concepts of karma and rebirth, or reincarnation. While not a direct equivalent to a physical multiverse, the idea of samsara, the endless cycle of birth, death, and rebirth across different realms of existence, presents a vision of multiple, simultaneous realities of experience. A single consciousness is not tied to one linear life, but can inhabit countless forms across countless worlds, from the blissful realms of deities to the suffering states of hell beings. This creates a kind of psychological and karmic multiverse, where every action ripples through a web of interconnected lives and realities. The emphasis is on the interconnectedness of all things and the potential for infinite journeys of the soul, a concept that resonates deeply with the modern scientific view of a cosmos where every possibility is realized. Drawing these connections between ancient wisdom and contemporary physics does not mean that Democritus had the mathematics right or that the Puranas describe cosmic inflation. Rather, it reveals something fundamental about the human spirit. We have an innate, timeless drive to look beyond the horizon of our immediate perception and ask what else might be out there. This urge to envision multiple realities seems to be a universal constant, as intrinsic to us as breathing. It emerges from a deep-seated need to understand our place in the cosmos, to find patterns in the chaos, and to challenge the limitations of a single, confined existence. The ancient philosophers used the tools they had: reason, metaphor, and spiritual insight. Today, we augment those tools with particle colliders and space telescopes. But the destination is remarkably similar: a humbling, awe-inspiring vision of a reality far grander and more diverse than our everyday experience suggests. This rich historical context does more than just add a layer of intrigue. It profoundly enriches our understanding of modern multiverse theory. It roots these seemingly fantastical scientific ideas in a broad, deep cultural narrative, showing that they are not a bizarre anomaly but a natural culmination of a human quest that has been underway for centuries. It grants the theory a certain weight and legitimacy, connecting the cutting edge of cosmology to the perennial questions that have always defined our species. Recognizing that the greatest minds across history and across cultures have arrived at similar conclusions about the plurality of worlds invites us to approach modern science not with skepticism, but with a sense of wonder at this long, collaborative, cross-cultural conversation about the ultimate nature of everything. This journey through time shows us that the universe of possibilities is not just a physical reality we are trying to map, but a fundamental part of how we have always tried to understand ourselves. But how does this grand cosmic perspective, this idea of infinite versions of ourselves, actually land in the quiet moments of our own minds? The concept of a multiverse isn't just an abstract theory for physicists to debate. It's a powerful psychological lens that can profoundly reshape how we view our own lives, our regrets, and our mental well-being. For some, learning about the many worlds interpretation can feel like a tremendous weight being lifted from their shoulders. That career path you didn't take, that relationship that ended, that painful word you wish you could take back instead of being locked away as singular, permanent failures in your personal history, they can be reframed as experiences that are being fully lived out by other versions of you in parallel timelines. The crushing finality of regret softens into a kind of cosmic curiosity. You didn't lose that opportunity, it simply unfolded in a different reality. This perspective can be a powerful antidote to anxiety and rumination, allowing you to release the grip on the past and be more present in the one timeline you are consciously experiencing, freeing you to make the most of the path you are actually on without being haunted by the ghosts of what might have been. However, for others, this exact same idea can trigger a deep and unsettling existential dizziness, a feeling that psychologists might call cognitive overwhelm. The notion that every trivial choice, from the sandwich you ordered for lunch to the route you drove to work, spawns an entirely new universe can make a person feel incredibly small and insignificant. If every possibility is realized, then what is the point of striving for anything? If a version of me is already a Nobel laureate and another is homeless, then does my effort in this timeline really matter? This line of thinking can lead to a kind of existential paralysis, a sense that individual agency is an illusion because all outcomes are preordained in the grand mosaic of the multiverse. It can feel isolating, knowing that your deepest joys and most profound sorrows are being experienced alone, with no other version of you able to share in that specific, singular experience. This isn't just philosophical pondering. It's a real emotional response to having the rug of a single, stable reality pulled out from under you. Psychologists who study narrative identity understand that humans are meaning-making creatures. We weave the events of our lives into a coherent story that gives us a sense of purpose and continuity. The multiverse concept directly challenges that by suggesting there is no single, true narrative, there are infinite narratives, all equally valid. Integrating this into a healthy world, you requires a conscious shift in focus, moving from a search for the one right path to a celebration of the unique path you are on. It's about practicing what we might call quantum mindfulness, cultivating curiosity about the other branches without feeling obligated to inhabit them. Instead of asking, "What if I had made a different choice?" you can learn to ask, "I wonder what that version of me is experiencing." This transforms envy or regret into a sense of wonder and even empathy for all your other selves. The goal isn't to become preoccupied with the infinite, but to use the idea as a tool to appreciate the finite, precious, and singular quality of your own conscious experience right here and now. It encourages a form of radical acceptance where you can acknowledge that while other paths exist, this is the one you are walking, and it deserves your full attention and care. While the ideas of eternal inflation and quantum branching paint a picture of a multiverse born from cosmic expansion and probabilistic events, there exists another, even more ambitious framework that attempts to weave these concepts into a single, all-encompassing tapestry of reality. This is string theory, and its implications for the multiverse are perhaps the most vast and mathematically stunning of all. To understand it, we need to reimagine the most fundamental building blocks of everything we see. For decades, we've thought of electrons and quarks as infinitesimal points, zero-dimensional dots with no internal structure. String theory proposes a radical shift. These are not points at all, but unimaginably tiny, vibrating loops of energy strings. And just like the string on a violin, the way each loop vibrates determines its properties. One specific vibration pattern makes it appear as an electron. A different frequency makes it a photon. Another creates a quark. In this elegant vision, the entire symphony of the universe, all the particles and forces, emerges from the music played by these fundamental strings. For this beautiful mathematical symphony to work, however, it requires a much larger stage than the 3 dimensions of space and one of time we are familiar with. The equations of string theory only produce stable, consistent results if we propose that the universe actually has 10 or 11 dimensions. So where are these extra dimensions? The theory suggests they are curled up or compactified into an exceedingly tiny, complex shape at every single point in space, far too small for us to ever perceive directly. Think of a long, thin garden hose. From a distance, it looks like a simple one-dimensional line, but if you get very close, you see it actually has a second dimension, its circular circumference. The extra dimensions of string theory are like that circular cross-section, but folded into intricate, multi-dimensional shapes called Calabi-Yau manifolds. The specific way these extra dimensions are folded is absolutely critical, because their geometry directly determines the laws of physics in the universe they inhabit. The shape dictates the number of particle families, the masses of electrons and quarks, the strength of gravity, and the value of the cosmological constant. Alter the shape even slightly, and you get a completely different set of physical laws. This is where the concept of the multiverse explodes into a landscape of literally unimaginable proportions. Because there is not just one unique way to curl up these extra dimensions, physicists like Leonard Susskind have explored the mathematics and found that the number of stable, possible configurations is astronomically vast. The estimate is around 10 to the power of 500. That's a 1 followed by 500 zeros. To say this number is astronomical would be a gross understatement. The number of atoms in the entire observable universe is only about 10 to the power of 80. The number of possible vacuum states in the string theory landscape is so colossally larger that it defies any human analogy. Each of these 10 to the 500 possible configurations corresponds to a universe with its own unique, self-consistent set of physical laws and constants. Our universe, with its specific particle masses and force strengths that allow for our existence, is just one single, tiny entry in this infinite cosmic catalog. We are not just one bubble in a foam. We are one specific combination lock setting in a warehouse containing more locks than there are atoms in the universe. This landscape multiverse provides a powerful, if controversial, potential solution to the problem of fine-tuning. Instead of asking why our constants are so perfectly set for life, we can simply say that every possible set of constants exists somewhere in the landscape. We, of course, find ourselves in one of the rare universes where the numbers happen to come out right. String theory doesn't predict our specific universe. It predicts all possible universes, and the Anthropic Principle does the rest of the work. This landscape represents one of the most significant attempts in modern physics to achieve the Holy Grail, a complete unification of quantum mechanics, which governs the very small, with general relativity, which describes gravity and the very large. By describing all forces and particles as vibrations of strings, including the hypothetical graviton which would mediate gravity, it aims to bring all of physics under one elegant mathematical roof. Yet, for all its breathtaking scope and mathematical beauty, string theory remains fiercely debated. A major criticism is that, so far, it has not produced any testable predictions that can be verified through experiment. The energy levels required to see direct evidence of strings or the extra dimensions are far beyond the capability of any particle collider we could ever hope to build. And with 10 to the 500 possibilities, the theory risks explaining everything and therefore predicting nothing specific about our own universe. Despite these challenges, it stands as a monumental intellectual achievement, a bold vision of reality that naturally and inevitably leads to a multiverse far more diverse and vast than any we have yet conceived. It pushes the very boundaries of what is knowable, forcing us to confront a cosmos of infinite variety and to question whether a final, single theory of everything must, by its very nature, describe not just our universe but all possible universes. But if these other bubble universes are out there, forever separated from our own by unimaginable stretches of eternally inflating space, how could we ever possibly hope to find a shred of evidence for their existence? This is the monumental challenge that transforms cosmology from pure theory into a grand detective story, and the most promising clue might be etched across the entire sky in the faintest of glows. This is the cosmic microwave background radiation, the oldest light in the universe. It's the cooled remnant of the Big Bang's fiery birth, a snapshot of the cosmos when it was a mere 380,000 years old, before the first stars or galaxies had even begun to form. This radiation fills every cubic centimeter of space, a cold whisper from the dawn of time with a temperature of just 2.7 degrees above absolute zero. For cosmologists, this isn't just ancient light, it's a fossilized imprint of the universe's infancy, and it may hold the secret to what happened even earlier, in the first incomprehensibly tiny fraction of a second. The CMB is incredibly uniform but not perfectly so. When we map it with exquisite precision using satellites like NAS, a WMAP, and the European Space Agency's Planck, we see it is mottled with tiny fluctuations, minute variations in temperature of just 1 part in 100,000. These tiny ripples are the seeds of all cosmic structure. The slightly denser regions would eventually collapse under their own gravity to form the vast web of galaxies and galaxy clusters we see today. But some scientists, like the team led by physicist Matthew Johnson at the Perimeter Institute, propose that these ripples might contain something even more extraordinary: the cosmic bruises from a collision with another universe. The theory of eternal inflation suggests our universe is one bubble in a frothing cosmic foam, and just like bubbles in a sink, they might occasionally bump into one another. If a neighboring bubble universe had collided with ours during its early, ultra-rapid inflationary phase, that impact would have sent a powerful shockwave, a ripple, through the fabric of our spacetime. That ripple would have left a distinct and potentially detectable signature on the CMB. So what exactly are these cosmic detectives searching for? They aren't looking for a random splotch. They're hunting for a specific, telltale pattern. A collision would not be a gentle nudge. It would be a directional event imparting a specific asymmetry to the cosmos. The most likely signature would be a distinct circular pattern of temperature variations, a kind of cosmic bullseye where the temperature changes in a specific, concentric way. Imagine the pattern a single raindrop makes on the surface of a pond. A bubble collision would leave a similar circular imprint, but on the fabric of the universe itself, frozen in time on the CMB. Researchers have developed sophisticated computer algorithms to scour the entire Planck satellite sky map, pixel by pixel, searching for these statistical anomalies, these faint circular patterns that deviate from the random fluctuations predicted by standard inflation. The hunt so far has been inconclusive but fascinating. A few years ago, an analysis of the WMAP data revealed several unusual features, including a large, mysterious cold spot, and some unexpected large-scale asymmetries that some researchers excitedly suggested could be potential candidates for a collision scar. However, when the higher-resolution Planck data was analyzed, these features largely faded into the background noise. They were statistical flukes rather than groundbreaking discoveries. No definitive, unambiguous bullseye has been found, but in science, a null result is not a failure, it is a refinement. Each time we rule out a class of collisions or a certain type of bubble universe, we tighten the constraints on our theories of inflation and the multiverse. We learn what the multiverse is not like, which is a crucial step toward understanding what it could be. This process is a powerful example of how our idea that was once purely metaphysical, the concept of other universes, is now being subjected to rigorous empirical testing. We are moving from asking, "Could this be?" to specifically defining, "If this is, what would it look like and how can we find it?" This incredible endeavor of searching for the fingerprints of other realities in the faint afterglow of our own birth highlights a profound shift in our relationship with the cosmos. We are no longer passive observers of the heavens. We are active forensic scientists, sifting through the evidence left from the very first moments of creation, looking for clues that point to a reality far grander and more interconnected than we ever dreamed possible. The very fact that we can pose these questions and devise methods to answer them is a testament to human curiosity and ingenuity, pushing the very limits of what we can perceive and understand. Yet for all its grandeur, this vision of an infinite multiverse runs headlong into a fundamental constraint, one that is not out there in the cosmos, but right here inside our own skulls. Our human brains are magnificent instruments, but they were not engineered by evolution to comprehend the true scale of quantum foam or the endless branching of cosmic inflation. We are creatures of the middle world, exquisitely adapted to navigate a reality of medium-sized objects moving at medium speeds over medium distances. We can instinctively judge the arc of a thrown rock, anticipate the behavior of a predator lurking in the grass, and understand the social dynamics of our tribe. These were the survival skills that mattered on the ancient savannah, grasping the reality that every single quantum decision spawns a new universe, or that our entire cosmos is one bubble in an infinite froth of others, requires us to think in scales and abstractions that are fundamentally alien to our innate cognitive toolkit. This is why multiverse theory often feels so deeply counterintuitive. It asks us to override the very operating system our minds have been running on for millions of years. Cognitive scientists who study how we conceptualize the unimaginable refer to this as the problem of scale. Our brains are brilliant at using analogy and metaphor to bridge the gap between the knowable and the unknown, but these tools have their limits. We might picture the multiverse as a vast tree with endlessly forking branches, or as an infinite ocean where each bubble is a universe. These are helpful starting points, but they are ultimately flawed. A tree exists in space and time. The multiverse may not be bound by such constraints. An ocean has a surface and a boundary. The multiverse likely does not. We are trying to use a middle-world vocabulary to describe something that exists entirely outside of middle-world experience, and the language will always fall short. This isn't a failure of intelligence, it's a limitation of our biological hardware. Our intuition, which serves us so well in daily life, becomes a source of error when venturing into the realms of the cosmically vast or the quantumly small, screaming that these ideas must be wrong because they feel wrong. This is where the true power of education and scientific reasoning reveals itself. The goal is not to somehow expand our brains to directly perceive higher dimensions or infinite branching. Rather, it is to build new mental models, scaffolding made from mathematics, logic, and disciplined thought that allow us to bypass the limitations of our intuition. We learn to trust the equations even when they contradict our gut feelings, because the equations have a proven track record of revealing truths about the world that our senses miss. We couldn't see the curvature of spacetime, but Einstein's math predicted it, and it was confirmed. We couldn't imagine quantum entanglement, but the math described it, and experiments have shown it to be real. In the same way, the mathematics behind eternal inflation and quantum decoherence point relentlessly toward a multiverse, providing a logically consistent framework that explains the world we see. Embracing this isn't about blind faith, it's about understanding that our perception is a narrow window, and mathematics is a telescope that allows us to see far beyond its frame. Acknowledging these cognitive limits is therefore not an admission of weakness, but a profound act of intellectual humility. It is the first step toward a deeper and more genuine curiosity. When we accept that the true nature of reality might be forever beyond our direct experience, we are freed from the arrogant assumption that the universe must conform to what we can easily understand. This humility opens the door to wonder. It allows us to sit with the discomfort of not knowing, to marvel at the mystery, and to appreciate the incredible fact that our middle-world brains, through ingenuity and perseverance, can nevertheless construct tools to uncover truths that are literally unimaginable. This journey from intuitive doubt to reasoned acceptance is one of the most thrilling adventures of the human mind, a testament to our unique ability to reach beyond our biological constraints and touch the edges of the infinite. Throughout our journey, we've relied on the language of physics to describe alternate realities, cosmic inflation, quantum waves, vibrating strings. But there is another, even more fundamental language that might provide the clearest window into these possibilities. A language that has consistently revealed the secrets of the universe long before we had the tools to observe them: mathematics. This isn't just about calculation, it's about revelation. Time and again, mathematicians have scribbled equations on a blackboard that described entities which seemed purely imaginary, only for physicists to discover them in nature decades or even centuries later. The concept of black holes emerged from Carl Schwarzschild's solutions to Einstein's equations of general relativity in 1916, a full half-century before the term black hole was even coined, and we found the first compelling evidence for their existence. The positron, the antimatter counterpart to the electron, was first predicted by Paul Dirac's work in 1928. A stunning discovery that seemed to come from the sheer elegance of his math rather than from experimental data. Mathematics has a mysterious and uncanny ability to be unreasonably effective in the natural sciences, as physicist Eugene Wigner once put it, as if we are just scratching the surface of a deep, pre-existing truth. This leads us to a profound philosophical question about the nature of mathematics itself. Are we inventing these concepts, crafting useful tools to describe the world we see? Or are we discovering them, uncovering eternal, immutable truths that exist independently of our minds? This is the central debate between mathematical invention and mathematical Platonism. A Platonist following the spirit of the ancient Greek philosopher Plato would argue that mathematical entities, the perfect circle, the concept of pi, the ideal prime number, have a real existence in a kind of abstract realm. They are not created by human thought, we merely stumble upon them. In this view, a mathematician is an explorer, not an inventor, charting the contours of a landscape that was always there. When we develop a complex new equation, we aren't creating something new so much as we are translating a timeless truth into a language our brains can understand. This perspective becomes incredibly powerful when we apply it to the multiverse. The vast mathematical landscapes of string theory, with their 10 to the 500 possible universes, aren't just interesting ideas we made up. To a Platonist, they are a map of a real, existing territory. Every single possible universe with self-consistent physical laws doesn't just exist as a possibility, it exists as a mathematical truth. Our particular universe is simply one that has been physically instantiated, one that has somehow been made manifest, while the others exist just as robustly in that abstract Platonic realm. The math isn't describing a possibility, it is describing a reality. This makes our mathematical equations something far more powerful than mere descriptions. They become veritable portals to other worlds. Every time a cosmologist writes down the equations for a universe with a different cosmological constant, or a physicist calculates the properties of a universe with 4 strong nuclear forces, they are, in a very real sense, peering into another reality. They are discovering what life would be like there, what the sky would look like, what forms matter and energy would take. The line between discovery and invention becomes beautifully blurred. Did we invent the idea of a universe with 2 time dimensions, or did we discover that the laws of mathematics allow for such a structure, and therefore it must have some kind of existence in the grand scheme of things? This isn't just academic navel-gazing. It suggests that the multiverse might be, at its heart, a mathematical structure. The physicist Max Tegmark takes this idea to its ultimate conclusion with his mathematical universe hypothesis, which proposes that our physical reality isn't just described by mathematics, it is mathematics. In this view, every self-consistent mathematical structure corresponds to a physical reality. Our universe feels real and physical to us because we are a self-aware substructure within a much larger mathematical object. This is a staggering concept. You, me, the stars overhead are all ultimately made of math. And if that's true, then every alternate reality we can describe with a self-consistent set of equations isn't just possible. It is every bit as real as our own, existing in a vast, abstract, and eternal mathematical multiverse. This incredible abstract journey, from the solidity of our world to the ethereal realm of mathematical truths, inevitably pulls us back to a far more practical and tantalizing question. If these other realities are in some sense real, whether as physical bubble universes or as mathematical structures, is there any conceivable way to reach across the void and make contact? Could we ever hope to send a signal or even receive one from a universe with entirely different laws of physics? The challenge is, of course, monumental. By their very definition, most models of the multiverse place these other worlds causally disconnected from our own. They are separated by unimaginable stretches of eternally inflating space, or they exist in their own separate quantum branches, or they are purely mathematical constructs with no physical bridge to our own. The very laws of physics that define our universe would likely prevent any known form of energy or information from crossing that boundary. A radio signal, a laser beam, a gravitational wave, all of these are phenomena that operate within the constraints of our local space-time and cannot transcend it. Yet the human imagination, fueled by the mathematics itself, refuses to be completely constrained. Some speculative theories have proposed potential loopholes. If the other universe is a quantum branch from our own, some interpretations suggest that the wave functions might not be completely disconnected. There might be faint, residual interference effects. While this wouldn't allow for sending a message saying hello, it might allow for a subtle statistical influence, a kind of whispering ghost in the machine of quantum probability. Another idea, even more speculative, involves the higher dimensions predicted by string theory. If our universe is a 3-dimensional membrane floating in a higher dimensional bulk, then it's theoretically possible that another universe brain could be floating nearby in that higher dimensional space. A gravitational wave, which is a ripple in space-time itself, might be the only force capable of leaking out of our brain, moving through the bulk and nudging a neighboring universe. This could potentially create a detectable signature, an unexplained gravitational anomaly in our universe that we might one day attribute to the close passage of another cosmic bubble. These ideas remain firmly in the realm of thought experiments, but they demonstrate how the desire to connect, to prove we are not alone in the grand multiverse, drives us to explore the very edges of physical law. Yet for all the seemingly insurmountable barriers that keep us isolated in our own cosmic bubble, the human mind refuses to accept permanent solitude. The tantalizing possibility of other realities inevitably leads us to a thrilling, if highly speculative, question: could we ever find a way to reach out and make contact? The challenges are, to put it mildly, monumental. By their very definition, most models of the multiverse place these other worlds in a state of perfect causal isolation. They are separated by unimaginable stretches of eternally inflating space that expands faster than light can travel, or they exist as decoherent quantum branches that have effectively stopped interacting with our own. The very laws of physics that govern our local reality would likely prevent any known form of energy, matter, or information from crossing that fundamental boundary. A radio signal, a laser beam, even a gravitational wave, all of these are phenomena that operate within the constraints of our local space-time and cannot transcend the void between separate universes. Despite these profound physical barriers, theoretical physicists have explored a few highly speculative loopholes that, while firmly in the realm of thought experiments, keep the dream of interuniversal communication alive. One intriguing idea revolves around the bizarre phenomenon of quantum entanglement. In our universe, we can create a pair of entangled particles whose properties are mysteriously linked, so that measuring the state of one instantly determines the state of the other, no matter the distance between them. Some have wondered if, at the precise moment of a quantum branching event, particles in the newly split universes might remain entangled with their counterparts across the divide. If such a cross-universe entanglement were possible, then manipulating a particle in our reality might theoretically cause a predictable change in its twin in another universe, creating a primitive form of Morse code tapped out across the multiverse. However, most physicists are deeply skeptical of this idea, as decoherence, the process that makes branches independent, seems to destroy any such quantum connections, effectively severing the link the moment the new universe is born. A more promising, though still fantastical, concept involves the higher dimensional spaces predicted by string theory. In this brain world scenario, our entire universe might be a three-dimensional membrane, or brain, floating within a higher dimensional volume called the bulk. Other universe brains could be floating in this same bulk, perhaps just a microscopic distance away in a higher dimension we cannot perceive, while the other fundamental forces, electromagnetism, the strong and weak nuclear forces, are thought to be confined to their home brain, gravity, by its very nature as the curvature of spacetime, might be able to leak out into the bulk. This opens up the remote possibility that a sufficiently powerful and precise gravitational wave generator in our universe could create ripples that travel through the bulk and gently perturb a neighboring brain. Conversely, an advanced civilization in another universe might be attempting the same thing, and we could one day detect an unexplained, anomalous gravitational vibration that defies all local explanation, a cosmic knock on the door from a reality next door. Perhaps the most famous thought experiment connecting the multiverse to practical computation comes from the visionary physicist David Deutsch. he proposed that a quantum computer doesn't just perform calculations incredibly fast, it effectively harnesses the computational power of parallel universes. The idea is that when a quantum computer enters a superposition of states to test many possible solutions to a problem simultaneously, it is delegating the work to copies of itself in alternate branches of the wave function. These parallel versions perform the calculations in their respective universes, and through the delicate magic of quantum interference, the results are combined to give the single correct answer in our universe. From this perspective, building a quantum computer is the first step toward a kind of practical, functional interaction with the multiverse. We may not be sending messages to other versions of ourselves, but we would be leveraging the existence of those other realities to perform tasks that are impossible for any classical machine. It's a form of communication not of words or pictures, but of computational resources, a silent, cooperative effort across the fabric of reality itself. While the practicalities of sending a message to another universe remain firmly in the domain of far future speculation, the very act of contemplating it yields immense value. It forces us to stretch our understanding of physics to its absolute limits, to question the true nature of causality and information, and to creatively explore the deepest implications of our best theories. This endeavor is not so different from the early days of radio, when pioneers like Marconi and Tesla were first figuring out how to send signals across the Atlantic, a feat that seemed like magic to their contemporaries. The philosophical implications are equally profound, challenging our notions of isolation and connection on the ultimate scale. It inspires a sense of cosmic curiosity that transcends the boundaries of our own reality, driving both scientific and philosophical inquiry forward. This relentless push to explore the impossible seamlessly leads us to the next great frontier, where the theoretical principles of the multiverse begin to converge with tangible, world-changing technology. This staggering potential of quantum computing moves us from the realm of abstract theory into the world of tangible, world-changing technology, and it all hinges on a principle that should now feel deeply familiar: superposition. Unlike a classical computer bit, which can only be a 1 or a 0, a quantum bit or qubit can exist in a state of both 1 and 0 simultaneously. This isn't just a minor technical upgrade, it's a fundamental reimagining of how information is processed. When you have multiple qubits interacting in this blurred state of possibilities, they enter a condition called quantum entanglement, creating a single, complex probabilistic state that represents all possible combinations of ones and zeros at the same time. This means a quantum computer doesn't perform calculations one after the other in a linear sequence. Instead, it explores a vast landscape of potential answers all at once in parallel. It's this mind-bending capability that leads physicists and programmers to half-joke that these machines are effectively borrowing processing power from alternate universes. While that's a playful metaphor rather than a literal explanation of how they work, it perfectly captures the revolutionary shift in thinking they represent. They are not just faster calculators, they are machines that operationalize the profound concepts of the quantum world, turning the bizarre logic of superposition into a practical tool. The real-world implications of this are already beginning to ripple across several critical fields, with cryptography standing as one of the most dramatic examples. The entire backbone of our digital security, from online banking to secure messaging, relies on encryption algorithms that would take a classical supercomputer thousands or even millions of years to crack through brute force calculation. A sufficiently powerful quantum computer, however, could theoretically solve these mathematical puzzles in a matter of hours or days, using specialized algorithms that exploit its parallel processing power. This looming threat, known as Y2Q, or the quantum apocalypse for digital security, has sparked a global race to develop a new generation of quantum-resistant encryption. But the story isn't just about breaking codes, it's also about creating new, unbreakable ones through quantum key distribution. This technology uses the principles of quantum mechanics itself to secure communication. If a third party tries to eavesdrop on a quantum encrypted message, their very act of observation would inevitably disturb the delicate quantum state of the particles carrying the information, immediately alerting the sender and receiver to the intrusion and causing the message to self-destruct. This is a breathtaking example of the observer effect being harnessed for practical security, turning a quantum quirk into a powerful shield. Beyond the digital realm, quantum computing promises to revolutionize material science and drug discovery in ways we can scarcely imagine. Simulating the behavior of molecules and atoms is an astronomically complex task for classical machines because they must model every possible interaction and state one at a time. A quantum computer, by contrast, can naturally simulate these quantum systems because it operates by the same rules. It can effectively become the molecule it is trying to study, holding all its possible configurations in superposition at once. This could allow researchers to design entirely new materials with tailored properties, super-efficient batteries, room-temperature superconductors, or ultra-strong lightweight alloys by virtually testing millions of atomic arrangements simultaneously. In medicine, it could dramatically accelerate the development of new pharmaceuticals by accurately modeling how a proposed drug compound will interact with a specific protein in the human body, bypassing years of costly and uncertain trial and error in the lab. These advancements demonstrate that the most abstract ideas in theoretical physics are not just intellectual curiosities. They are the seeds of technological revolutions that can redefine human civilization, pushing the boundaries of what we once believed was possible and giving us new tools to solve our most pressing challenges. Yet, as with any transformative power, this one arrives with a profound ethical weight. The ability to manipulate reality at the quantum level, to harness the power of parallel possibilities, forces us to confront new moral dilemmas. If we can one day use quantum sensors to peer into the previously invisible quantum world with incredible precision, what are the privacy implications? Could such technology be used to develop surveillance systems that bypass traditional encryption or perceive the world in ways that eliminate any concept of private thought? The potential for a quantum advantage in fields like artificial intelligence is equally double-edged. An AI powered by a quantum computer could solve optimization problems for global logistics, climate modeling, or economic planning that are currently intractable, potentially leading to a new era of efficiency and prosperity. But that same power could also be directed toward creating unprecedentedly powerful autonomous weapons or social control systems. The act of manipulating quantum states, of literally bending probability to our will, is not a neutral act. It demands a parallel advancement in our ethical frameworks, a proactive and global conversation about how to guide this technology toward benevolent ends before its capabilities outstrip our wisdom. This responsibility ensures that our boundless curiosity is matched by a deep sense of care for the future we are actively creating. But the power to manipulate reality, whether through quantum technologies or hypothetical future devices that could peer into alternate branches, carries with it an immense and sobering ethical weight that we are only beginning to contemplate. Imagine for a moment that we develop a technology, perhaps a sophisticated quantum sensor, that allows us to not just infer the existence of other branches, but to weakly observe them, gathering data about the choices and outcomes of our other selves. The immediate question becomes one of consent. Do those other versions of us, living their lives in what they believe to be their own private, singular reality, have any right to privacy from our observation? If we can see the devastating consequences of a poor decision in another timeline and use that information to guide our own choices, are we benefiting from their suffering without their knowledge or permission? This isn't just a theoretical puzzle. It strikes at the very heart of autonomy and the right to a self-determined existence, even for a version of you that you may never meet. This leads directly to the even thornier issue of interference. What if our technology advances beyond mere observation to a point where we could send a faint signal, a piece of information across the quantum divide? If you could warn another version of yourself about an impending disaster, a health diagnosis they missed, a financial mistake they are about to make, a relationship that will end in heartbreak, would you have a moral obligation to do so? On one hand, it seems the ultimate act of altruism, preventing suffering for a being that is, in a fundamental sense, you. But on the other hand, such an act would be a profound violation of their personal journey. Their life, with all its triumphs and failures, is their own to experience. Our interference, however well-intentioned, would rob them of their agency, effectively imposing our will and our timeline's preferences onto their independent existence. It would be the ultimate form of paternalism, potentially creating a paradox where we feel responsible for managing an infinite number of lives across the multiverse, a burden no single consciousness could ever bear. We must also grapple with the law of unintended consequences, a principle that becomes exponentially more dangerous when applied across the fabric of reality. A seemingly benign adjustment in one universe could have catastrophic ripple effects that we could never predict. A warning meant to prevent a single car accident in another branch might inadvertently alter a chain of events that leads to a different, far greater tragedy. Our understanding of cause and effect is based on the linear, localized physics of our own universe. We have no model for predicting how a change in one quantum branch might destabilize others. This isn't like time travel paradoxes in movies. It's a complex systems problem on a literally infinite scale. The ethical precautionary principle would suggest that the only safe course of action is one of non-interference, a cosmic prime directive that respects the sanctity and isolation of each individual timeline, allowing the vast tree of possibilities to grow naturally without our pruning. These questions force us to expand our ethical frameworks beyond our own world and even our own species, to consider a truly cosmic bioethics. The debates we have today about genetic engineering, artificial intelligence, and environmental stewardship are rehearsals for a much larger conversation about our role and responsibilities as a conscious force in the multiverse. Do we have a duty to nurture life and foster flourishing not just on Earth, but in any universe where we can potentially have an influence? Or does that duty compel us to stay our hand, to recognize that the most ethical stance is one of humility and non-intervention? This proactive discourse is not a distraction from scientific progress. It is an essential part of it. By grappling with these questions now, before the technology is even a reality, we build the moral scaffolding needed to ensure that our boundless curiosity is always matched by a deeper sense of wisdom and responsibility, ensuring that as our power grows, our compassion and foresight grow with it. For countless individuals across the globe, the idea of multiple realities is not a new or shocking scientific proposition, but a deeply held article of faith that has provided comfort and context for millennia. Within the world's great spiritual traditions, the concept that our existence is not confined to a single, linear lifetime or a solitary plane of being is a foundational truth. Christianity and Islam speak of multidimensional realms like heaven, hell, and purgatory, distinct realities operating under different spiritual laws, awaiting souls after death. Hinduism and Buddhism present a vast cyclical cosmology of reincarnation and countless worlds, known as lokas, where consciousness journeys through an immense spectrum of experiences across many lives. Indigenous animist beliefs often include spirit worlds that exist alongside our own, accessible through ritual or altered states of consciousness. These are not seen as metaphorical stories, but as descriptions of a genuine, layered reality that interacts with our own in meaningful ways. What is truly fascinating is how the modern scientific multiverse theory doesn't necessarily dismantle these ancient beliefs. Instead, it can provide a new, complementary framework that allows for a harmonious dialogue between the laboratory and the chapel. For a person of faith, the notion that God's creation might be infinitely vaster and more complex than a single universe encompassing a boundless multiverse where every possible form of existence is realized can be seen as a magnificent affirmation of divine omnipotence and creativity, not a challenge to it. The scientific mechanism of eternal inflation or quantum branching becomes the how, while the spiritual purpose remains the why. This perspective allows an individual to fully accept the findings of cosmology and quantum physics without feeling they must abandon their spiritual identity. They can see the Big Bang as the moment of creation and the multiverse as the breathtaking canvas upon which that creation unfolds. This isn't about forcing a fit. It's about recognizing that science and spirituality are two different languages attempting to describe the same profound mystery, one through mathematics and observation, the other through revelation and experience. This integration fosters a powerful and much-needed inclusive approach to some of humanity's biggest questions. When a Buddhist monk contemplates the innumerable world systems described by the Buddha, and a cosmologist contemplates the inflationary bubble multiverse, they are, in a sense, standing on common ground, gazing at the same staggering immensity from two different vantage points. This shared awe can become a bridge for respectful dialogue, where the goal is not to convert or debunk, but to understand and appreciate different ways of knowing. It encourages a humility that is essential for both the scientist and the theologian, reminding each that their models are ultimately limited, human attempts to grasp a reality that may forever hold an element of the ineffable. This convergence allows for a more personal and nuanced spirituality, one where belief in a soul's journey through multiple lives or realms can coexist with an appreciation for the physical laws that might govern such an incredible voyage. Now, let's take this extraordinary idea out of the lab and the lecture hall and drop it right into the middle of our daily lives. Imagine waking up one morning to a news alert so profound it redefines the word reality itself. Major scientific organizations from CERN to NASA are holding a joint press conference. The evidence is undeniable and overwhelming. They have confirmed the existence of other universes. Not as a mathematical possibility, but as a physical fact. The headlines scream, the social media feeds explode, and in that single moment, the collective understanding of every human being on the planet shifts irrevocably. This wouldn't be like the discovery of the Higgs boson or gravitational waves, events that thrilled the scientific community but remained abstract for most. This would be a paradigm quake, a fundamental reshaping of our entire worldview that would ripple through every layer of society, from our education systems and legal frameworks to the very core of our personal identities. The first and most immediate impact would be a seismic shift in education. Textbooks from elementary school to postgraduate levels would become instantly obsolete. Science classes would no longer present a single, linear history of our universe, but a sprawling, multi-branched narrative. History lessons would have to be reimagined entirely, taught not as a fixed record of what happened, but as one possible narrative thread in an infinite tapestry of what could have happened. The very purpose of education would subtly change, moving from memorizing a set of established facts to cultivating a new kind of mental flexibility, the ability to hold multiple, contradictory truths in mind simultaneously, to think in terms of probabilities and possibilities rather than certainties. This would require a monumental effort in retraining teachers and redesigning curricula, a challenge akin to the intellectual revolution that followed the widespread acceptance of a heliocentric solar system, but happening at the speed of the internet. This revolution would inevitably spill over into our legal and justice systems, presenting philosophers and lawmakers with dilemmas we can barely conceive of today. Our entire concept of law is based on cause and effect within a single, deterministic timeline. But how do you assign blame and responsibility in a multiverse? If a person commits a crime, but in a nearly identical branch universe a version of them did not, to what extent are they truly responsible? Defense attorneys might argue that their client is simply the version of themselves who, through no fault of their own, ended up on the branch where a tragic quantum fluctuation led to a poor decision. This isn't about evading justice, it's about forcing a complete re-evaluation of free will, culpability, and the very purpose of punishment. Would the goal of the justice system shift from retribution to rehabilitation, focusing on ensuring that this version of a person walks a better path forward, knowing that other versions already are? The societal debates would be fierce, profound, and would touch on the deepest questions of what it means to be a moral agent. On a deeply personal level, the confirmation of alternate selves would trigger a global identity crisis, followed by what could be a great liberation. The notion of a single, authentic you would dissolve. You would no longer be just the sum of your choices in this timeline, but one manifestation of a vast quantum network of potentialities. For some, this could be initially destabilizing, causing feelings of insignificance or existential anxiety, but for many, it could be an incredible weight off their shoulders. Regret over past mistakes could transform into curiosity about the paths of other selves. The pressure to find your one true purpose in life would ease, replaced by the understanding that you are living out one of countless valid expressions of your potential. This could foster a new culture of self-acceptance and reduce the social stigma around failure, as every failure here is a success in another reality. People might become more adventurous, more willing to take calculated risks, knowing that in the grand scheme of the multiverse, no door ever truly closes. Economically, the potential is staggering. While physical travel to another universe might remain forever in the realm of fantasy, the mere confirmation of their existence would birth entirely new industries. The first would be information-based. What would we call it? Cosmic anthropology, comparative universology. We would launch sophisticated new telescopes and sensors not to look at stars, but to peer across the dimensional divides, attempting to map the laws and histories of our closest neighboring realities. The data gathered would be incomprehensibly valuable, and the field would attract trillions in investment from governments and private entities eager to gain any advantage. Entertainment and media would be utterly transformed. Imagine virtual reality experiences that don't just simulate fantasy worlds, but are based on real data from alternate Earths, allowing you to walk through a world where the Roman Empire never fell or where your own life took a different turn. The storytelling possibilities would be infinite, and a new art form would emerge dedicated to exploring and narrating the lives of our alternate selves. History shows us that great paradigm shifts from Copernicus to Darwin are initially disruptive and often met with resistance, but they are ultimately enriching. They force us to grow, to adapt, and to see ourselves as part of a much larger, more magnificent story. The confirmation of a multiverse would be the greatest such shift in human history. It would be messy, confusing, and challenging on a global scale, but it would also be the ultimate catalyst for a new era of human creativity, compassion, and cosmic curiosity. It would prepare our species not just for a future on this planet, but for a future where we finally understand our true place in a reality without limits. This expansive view of our existence inevitably makes us reconsider our responsibilities, not just to our world, but to all potential worlds, leading us to a crucial conversation about the environment on a multiversal scale. On the surface, the existence of a multiverse teeming with infinite Earths could be twisted into the most perilous excuse for inaction ever conceived. Why sweat over rising sea levels, melting ice caps, or vanishing species if, somewhere out there, a pristine version of our planet is doing just fine? It's a seductive line of thinking, a potential license for ecological nihilism that suggests our specific world is disposable, just one copy in a cosmic library where every story is written. But this perspective is not only flawed, it tragically misses the profound ethical upgrade that the multiverse concept actually demands of us. This isn't about finding an escape hatch for our failures. It's about recognizing that our responsibility is magnified, not diminished, by the sheer scope of existence. Think of it not as having infinite copies, but as being the curators of a singular, irreplaceable masterpiece in a gallery of endless variations. Yes, there may be other versions of the Mona Lisa, but that doesn't make the one hanging in the Louvre any less priceless. Its value is inherent in its unique history, its specific brushstrokes, its journey through time. Our Earth is that masterpiece. This is the only version of our home that contains the precise evolutionary path that led to us, that holds the specific cultural heritage of every human who has ever lived, that cradles the memories of our personal lives and loves. The biodiversity we are losing, each unique species of frog, each variety of orchid, each unknown insect in the rainforest, is not being lost in a generic sense. It is the loss of a specific, intricate thread in a tapestry that will never be woven in exactly the same way again, anywhere. The multiverse doesn't make this loss commonplace. It highlights the breathtaking uniqueness of what we are custodians of right here and now. Furthermore, this expanded view forces us to consider a chilling and deeply empathetic possibility. For every Earth that thrives, there might be another facing an ecological apocalypse. If the many worlds interpretation is correct, then there are branches where climate change was ignored completely, where industrial pollution ran utterly unchecked, and where civilizations collapsed under the weight of their own unsustainable consumption. In those realities, versions of us, beings who share our consciousness, our hopes, and our capacity for suffering, are experiencing the direct consequences of choices we, in this timeline, managed to avoid. This knowledge should not be a comfort. It should be a sobering warning and a call to compassionate action. Our successful stewardship of this planet isn't just about us. It becomes a symbolic victory for the potential of intelligent life everywhere to choose a sustainable path. We are proving it can be done, that a technological species can live in harmony with its world. By protecting our environment, we are honoring the struggle of those other selves in less fortunate timelines and affirming the value of life against the indifferent vastness of the cosmos. Ultimately, the multiverse perspective shatters the outdated idea that we are separate from our environment. We are not visitors on this planet. We are an emergent property of it. Our consciousness is quite literally the universe becoming aware of itself through the complex biological system that is Earth. To damage that system is to damage the very vessel that allows for awareness and meaning to exist. Therefore, environmental ethics in a multiverse becomes the highest form of self-preservation. It is the understanding that protecting the intricate, delicate web of life on this specific world is synonymous with protecting the possibility of experience itself. This realization connects directly to our search for other habitable worlds, not as potential replacements, but as fellow masterpieces in the cosmic gallery, each one deserving of the same reverence and awe we are learning to grant our own. For centuries, gazing up at the stars, we could only wonder if other worlds like our own existed out there. It was a question for philosophers and dreamers. Then, in the last few decades, astronomy underwent a revolution. With the launch of missions like NASA's Kepler Space Telescope, we moved from speculation to discovery. Kepler's entire purpose was to stare relentlessly at a single patch of sky, monitoring the brightness of over 100,000 stars, looking for the telltale, periodic dimming that occurs when a planet passes in front of its sun. This painstaking work paid off in a way that stunned even the most optimistic scientists. We didn't just find a handful of planets, we found thousands, revealing that planets are not the exception but the rule in our galaxy. The cosmos is teeming with them, and among this vast celestial census, the most thrilling discoveries are the exoplanets that fall within what we call the habitable zone, the orbital distance from a star where temperatures might be just right for liquid water to exist on a rocky surface. These are the worlds that spark our imagination, the potential Earths 2.0. Now, let's layer this incredible discovery onto the concept of the multiverse. If our single universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, and a significant fraction of those stars host planets, then the number of potential Earth-like worlds is already astronomically large. But the multiverse idea takes this and expands it to a literally infinite degree. In an infinite multiverse, there isn't just one Earth analog orbiting a sun-like star. There are endless variations. Imagine an Earth where the asteroid never struck and dinosaurs evolved into a sophisticated, tool-using civilization. Picture an Earth where the ancient supercontinent of Pangaea never broke apart, creating a single, massive biome with an entirely unique evolutionary history. Consider an Earth where the Moon formed differently, resulting in a much slower rotation, with days that last for weeks, and life forms adapted to long periods of light and darkness. In the multiverse framework, these aren't just imaginative stories, they are statistical certainties. Every possible geological history, every potential evolutionary pathway, every twist of climate and fate is playing out on a version of our world somewhere in the cosmic ensemble. This is where our most powerful new tool, the James Webb Space Telescope, becomes absolutely central to the narrative. While Kepler was a planet hunter, Webb is a planet analyzer. Its incredible infrared sensitivity and massive mirror allow it to do something that was once pure science fiction. It can capture the faint starlight that filters through the atmosphere of a distant exoplanet. By dissecting that light into a spectrum, scientists can identify the chemical fingerprints of gases present in that alien air. The Holy Grail is to find a combination of gases that strongly suggest biological activity, a biosignature. This might be the simultaneous presence of oxygen and methane, which normally react and destroy each other unless something like life is constantly replenishing them. Or it could be a more complex cocktail of gases that doesn't make sense through geology alone. Finding such a signature on just one exoplanet would be the most profound discovery in human history, proving that we are not alone. But from a multiverse perspective, a single discovery would be just the first data point. The true goal is a larger survey, a census of exoplanet atmospheres, If we find that life is incredibly rare, that only 1 in a million Earth-like worlds shows a biosignature, that tells us one story about the uniqueness of our existence. But if we find that biosignatures are common, that life seems to emerge almost everywhere the conditions are vaguely right, that tells a completely different story. It would powerfully support the multiverse principle that, given enough opportunities, every possible outcome, including the emergence of life, becomes not just possible but inevitable. Webb is essentially taking the first tentative steps toward testing the Anthropic Principle on a galactic scale, gathering the data that will help us understand if our universe is a rare, finely tuned oasis, or just one particularly successful example of a universal law of biology. This grand search does more than just advance science. It captivates the public imagination in a way few other endeavors can. The announcement of a new potentially habitable world sends a ripple of excitement across the globe. It taps into our most fundamental curiosities about who we are and where we belong in the cosmos. Each new discovery, each blurry spectrograph from a world light years away, is a Rorschach test onto which we project our hopes, our fears, and our dreams of connection. It fuels a sense of shared adventure, a collective endeavor to understand our place in a reality that grows vaster and more wonderful with every passing observation. This ongoing exploration, this relentless search for our twin in the void, is the most tangible and thrilling expression of our desire to peer beyond the horizon of our own universe and into the infinite possibilities that may lie beyond. So we find ourselves standing on the shoulders of giants, peering out into a galaxy that science tells us should be overflowing with life, with billions of Earth-like planets in the Milky Way alone, and many of them billions of years older than our own. The cosmos should be a bustling interstellar metropolis, filled with the radio chatter of countless civilizations. And yet, when we train our most powerful telescopes on the heavens, we are met with a profound and unsettling silence. This glaring contradiction between the high probability of extraterrestrial life and the complete lack of any evidence for it is one of the most enduring mysteries in science, known as the Fermi paradox, named for the physicist Enrico Fermi, who famously asked, "But where is everybody?" The multiverse framework offers a fascinating and deeply humbling set of answers to this question, reframing our lonely silence not as a paradox but as a selection effect. The first and most straightforward explanation is that the vast majority of universes in the multiverse are simply sterile. While our universe has the Goldilocks perfect constants for life, this might be an exceedingly rare occurrence. In most other bubble universes, the strength of gravity or the nuclear forces are so misaligned that atoms never form, stars never ignite, and the cosmic story ends before the first chapter even begins. In this view, we shouldn't be asking why we don't see life everywhere. We should be marveling that we exist to ask the question at all. Our universe isn't silent because life is rare. Our universe is one of the very few that is even capable of making a sound. Another chilling possibility is that the Great Filter, a hypothesized event or barrier that prevents life from progressing to an interstellar stage, is not behind us but ahead of us. Perhaps the evolution of intelligent, technological life is relatively common, but the transition to a stable, spacefaring civilization is almost impossible to achieve. In an infinite multiverse, this means there are countless versions of Earth where civilizations just like ours reached our level of technology, only to be wiped out by the weapons they created, or the ecological collapse they triggered, or some other unforeseen consequence of their own advancement. The silence we hear could be the echo of countless failures, a cosmic graveyard of worlds that never made it past their technological adolescence. This multiverse perspective turns the Fermi paradox into a sobering warning. We may not be hearing from anyone else because no one else has ever managed to survive what we are now going through. There is a third, even more mind-bending multiverse solution. It's possible that advanced civilizations do exist and are thriving, but they have transitioned into forms of existence that are completely undetectable to us. Perhaps they have uploaded their consciousness into vast computational networks, living in customized virtual realities that require no interstellar travel. Or maybe they have mastered the physics of higher dimensions, moving through realities we cannot perceive. In a multiverse of infinite possibilities, the ways an intelligence could evolve are beyond our imagination. The reason we don't see them is not because they aren't there, but because we are like ants on a sidewalk, unaware of the human world of cities and satellites just above us. Our search for radio signals and Dyson spheres might be looking for the equivalent of stone tools and smoke signals, completely missing the true signature of a post-biological, post-physical intelligence. This incredible capacity of multiverse theory to provide plausible, testable frameworks for solving ancient puzzles is what makes it so powerful. It doesn't just add more speculation, it adds more layers of understanding, allowing us to think about problems in a completely new way. The Fermi paradox is no longer a single, frustrating question, but a branching tree of potential answers, each one leading us to a deeper appreciation of our own precarious and precious place in the cosmic order. This same multiverse thinking now prepares us to confront the two most mysterious components of our own universe, entities so dominant that they shape the fate of all cosmos, yet remain almost entirely hidden from our view. And yet, for all its profound influence, dark matter remains one of the most vexing mysteries in all of science. We can map its gravitational footprint. We can see how its immense weight bends the light from distant galaxies like a cosmic lens, but we have no idea what it actually is. Is it a sea of exotic, undiscovered particles that barely interact with normal matter, known as WIMP? Or could it be primordial black holes formed in the chaotic first second after the Big Bang? Decades of sophisticated experiments, from deep underground detectors to powerful particle colliders, have so far come up empty-handed in the direct hunt for its identity. This profound ignorance is where the multiverse concept swings the door wide open. If the properties of dark matter are not fixed by a single, universal law, but are instead the result of random chance during the formation of each bubble universe, then its behavior could be one of the key variables that makes each reality unique. In our universe, we just happen to get a type and an amount of dark matter that allows for the graceful formation of grand spiral galaxies. But what if in another universe, dark matter is too weak? Without its gravitational scaffolding, ordinary matter might never clump together effectively, resulting in a lonely, diffuse cosmos where stars and planets never form, a silent and dark expanse where the lights of life never switch on. Conversely, what if another universe got a much stronger, more aggressive form of dark matter? Its overwhelming gravitational pull might cause matter to collapse too quickly and violently, triggering a frenzy of star formation that burns through a universe's fuel in a cosmic blink, leaving behind a graveyard of black holes and dead stars long before any delicate process like biology could ever begin. The specific recipe for dark matter in a given universe could be the ultimate determining factor between a vibrant, long-lived cosmos and a stillborn one. Now, let's turn to the even more bizarre and dominant force shaping our cosmic destiny, dark energy. This is the name we give to whatever is causing the expansion of our universe to not just continue, but to accelerate. Imagine throwing a ball into the air, only to watch it not just keep going up, but fly away from you faster and faster, defying gravity itself. That's the effect dark energy has on the very fabric of space-time. It acts as a kind of anti-gravity, a repulsive force embedded in the vacuum of empty space itself, and it makes up a staggering 68% of the total mass energy content of the cosmos. Its discovery at the turn of the millennium was so shocking and counterintuitive that it earned a Nobel Prize, completely upending our previous models of a universe that would gradually slow its expansion. Yet, like dark matter, we are completely in the dark about its fundamental nature. Is it a manifestation of Einstein's cosmological constant, a fixed property of space, or is it a dynamic energy field that has changed over time, known as quintessence? The multiverse perspective offers a breathtakingly simple explanation for one of the biggest puzzles surrounding dark energy: its seemingly improbably small, yet perfectly tuned value. Theoretically, the strength of dark energy could have been 120 orders of magnitude stronger than what we observe. If it were, its repulsive force would have been so powerful in the early universe that it would have ripped apart every proton, atom, and molecule before they could even form, instantly tearing any potential for structure to shreds. The fact that our dark energy is so inexplicably weak, allowing galaxies to coalesce and life to emerge, has long been considered one of the ultimate examples of cosmic fine-tuning. But in the landscape of the multiverse, this fine-tuning vanishes. In this view, the value of the dark energy density isn't a law. It's a roll of the cosmic dice, a random parameter set during the inflationary birth of each bubble universe. The vast, overwhelming majority of universes would have a value for dark energy that is either too strong, leading to a catastrophic big rip, or effectively zero, leading to a universe that recollapses in a big crunch long before life can arise. We find ourselves in one of the incredibly rare bubbles where the number, by pure chance, came out just right, small enough to allow for galaxy formation, but present enough to drive the accelerated expansion we see today. Dark energy, therefore, isn't a puzzle to be solved in our universe alone. It is the primary engine of diversity across the multiverse, a dial that gets randomly turned to a different setting in each new bubble, determining its ultimate fate and its potential for creating complexity. Understanding the interplay between these two dark components could very well be the master key that unlocks the deepest secrets of reality's architecture. They are the invisible hands that sculpt the cosmos on the largest scales, governing the birth, life, and death of entire universes. The quest to identify dark matter and to comprehend the nature of dark energy is more than just filling in the blanks in our textbooks. It is an attempt to read the rulebook of the multiverse itself, to understand the range of possibilities that physical reality can manifest. Every new observation, from the deep field surveys of the James Webb Space Telescope to the precise measurements of the cosmic microwave background, is giving us a clearer picture of how these forces have shaped our own particular cosmic story. And with each step forward, we gain a richer appreciation for the incredible luck of our own existence in a universe where the dark components conspired, just by chance, to create a stage vast, stable, and long-lived enough for us to appear and to begin asking these very questions. This profound investigation into the dark underpinnings of the cosmos naturally leads us to an even more radical idea at the forefront of theoretical physics, a principle that suggests the reality we perceive might be nothing more than a spectacularly detailed projection. Just when we thought our understanding of reality couldn't get any more bizarre, physics invites us to consider a possibility that sounds like it's been lifted straight from the pages of a science fantasy novel. What if the universe you think you're living in, with its rich three-dimensional depth, the solidity of the ground beneath your feet, the vast star-filled expanse above, is nothing more than an incredibly convincing illusion? What if everything we see, touch, and experience is actually a magnificent projection, a cosmic hologram emanating from a flat, two-dimensional surface at the very edge of our perception? This is not a philosophical thought experiment. It's a serious scientific proposal known as the Holographic Principle, and its origins are as grounded in real physics as they are astonishing. The story of this incredible idea begins not with holograms, but with one of the most destructive objects in the universe, black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery while studying these gravitational monsters. He realized that a black hole's entropy, which is a measure of its information content or disorder, was not proportional to its volume, as one might expect for a three-dimensional object. Instead, it was proportional to the surface area of its event horizon, the two-dimensional point of no return. This was a profound clue that the information describing everything that ever fell into the black hole wasn't lost inside its mysterious interior, but was somehow encoded on its two-dimensional boundary. Later, Leonard Susskind and Gerard T. Hooft took this concept and ran with it, proposing that this might not be a weird property unique to black holes, but a fundamental principle of the universe itself. They suggested that all the information needed to describe a three-dimensional volume of space can be entirely contained on its two-dimensional boundary. Think of it like a holographic sticker on your credit card. That sticker is a flat, two-dimensional surface, but when you tilt it under the light, it projects a stunning image with apparent depth and dimension. The holographic principle argues that our entire universe is that projected image, and the real data, the ultimate source code of reality, is stored on a distant two-dimensional surface we can't see. This leads to a staggering implication. Information is not just something we process in the universe. Information may be the universe. At the most fundamental level, reality might not be made of tiny, solid particles, but of bits, of yes/no answers to quantum questions. The solidity of your desk, the warmth of the sun, the sound of a voice, all of it could be the emergent property of an unimaginably vast and complex information processing system happening on a flat surface at the edge of spacetime. It suggests that what we perceive as physical reality is a kind of user interface, a convenient rendering that our brains have evolved to interpret, while the true workings of the cosmos are a dizzyingly complex dance of data on a two-dimensional screen. This idea forces us to question the very nature of what is real. If the universe is a projection, then the distinctions we hold so dear, between past and future, between here and there, even between you and the rest of the cosmos, might be secondary, emergent phenomena, not primary truth. Now, let's cast this incredible idea against the backdrop of the multiverse. If our universe is a holographic projection from a two-dimensional surface, then what's to stop there from being other surfaces projecting other universes? In the landscape of string theory or the foam of eternal inflation, each distinct bubble universe could be its own unique holographic projection, emanating from its own two-dimensional boundary. Our universe, with its specific laws of physics and constants, would be one specific projection, one particular movie being played from the cosmic data encoded on our boundary. Another universe with entirely different physical laws would simply be a different movie being projected from a different two-dimensional surface. This provides a breathtakingly elegant mechanism for the existence of a multiverse. The deeper reality isn't an infinite collection of three-dimensional bubbles. It's an infinite collection of two-dimensional surfaces, each one storing the information for an entire cosmos, with our perceived reality being nothing more than a spectacularly detailed shadow play. This perspective doesn't just challenge our understanding of space, it forces us to completely re-evaluate our most fundamental experience of existence, the relentless one-way flow of time. But if the very fabric of reality might be a holographic projection, then what does that say about one of our most fundamental experiences, the relentless one-way flow of time? We take for granted that time moves forward, an irreversible arrow flying from a fixed past toward an uncertain future. We remember yesterday but not tomorrow. We can break an egg but never unbreak it. This intuitive directionality is so ingrained in our existence that it feels like an absolute law of the cosmos. Yet, the bizarre truth is that the fundamental equations of physics, from Newton's mechanics to Einstein's relativity to Schrödinger's quantum equation, work perfectly well whether time runs forward or backward. There's nothing in these core laws that pins down the arrow of time. So why does our universe exhibit such a strong preference for one direction? The key to this mystery lies in a concept called entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It's this statistical tendency toward disorder that gives time its arrow. Think of a neat sandcastle on a beach. Left to the elements, it will inevitably crumble into a disorganized pile of sand, a state of higher entropy. It's incredibly unlikely for the wind and waves to spontaneously arrange that scattered sand back into a perfect castle. The universe is like that on a grand scale, moving from a state of low entropy at the Big Bang toward a future of maximum disorder, an eventual fate known as the heat death of the cosmos, where energy is evenly distributed and nothing ever happens again. Our perception of time's flow is essentially us riding this wave of increasing entropy, witnessing the universe becoming more disordered. Now, let's launch this understanding into the multiverse. If our universe's arrow of time is a consequence of its specific initial conditions, an incredibly low entropy starting point, then other bubble universes could have begun with entirely different setups. Imagine a universe that was born in a state of maximum entropy, a state of perfect and boring equilibrium. In such a place, there would be no gradient, no drive toward greater disorder, and therefore no arrow of time at all. For any conscious being that might hypothetically exist there, the concepts of past and future would be meaningless. Their entire reality would be a single, static, eternal moment. Another possibility is a universe where the initial low entropy state was configured differently, causing the arrow of time to point in the opposite direction from ours. From our perspective, such a universe would appear to be running backward. But from the perspective of a consciousness within that universe, their experience would feel perfectly normal. They would remember what we would call their future and anticipate what we would call their past to them. A broken egg would spontaneously reassemble, and a dispersed perfume would gather back into its bottle. Their psychological arrow of time would be aligned with their thermodynamic arrow, just as ours is, even though they are pointing in opposite directions. This leads us to some of the most ancient and profound cosmological ideas, now recontextualized through a multiverse lens. The concept of eternal recurrence, explored by philosophers like Nietzsche and ancient cultures alike, proposed that the universe cycles through identical periods of birth, death, and rebirth. In a multiverse context, this could be a reality where the cosmological constants lead to a big crunch, a recollapse of the universe so perfectly symmetric that it triggers a new Big Bang, starting the cycle all over again with the same initial conditions each time. In this cyclical model, time is not a line but a circle, with every event destined to repeat itself infinitely. A different model favored by many physicists is the static block universe. In this four-dimensional picture, time is an illusion. The past, present, and future all exist simultaneously in a fixed, unchanging structure. our conscious experience of moving through time is just a peculiar way our brains process this single, eternal block. The multiverse, then, would be a vast collection of such blocks, each with its own unique four-dimensional geometry. Some might be linear like ours, others cyclical, and still others might have complex, branching structures that defy any simple description. This radical variability of temporal experience completely shatters our linear perception of history and future. It means that our narrative of cause and effect, of a clear progression from one event to the next, is not a universal truth but a local byproduct of our universe's particular physics. It forces a profound humility, reminding us that our most basic experiences are not the standard for all of reality, but merely one possible configuration in an infinite ensemble. Understanding that time itself is fluid and variable is the final, crucial step in expanding our minds to grasp the next great frontier, the mind-bending possibility of realities with more than the three spatial dimensions we call home. But to truly grasp the reality of these extra dimensions, we need to step beyond the math and into a thought experiment. Imagine a world of absolute flatness, a universe of only two dimensions like the pages of a book. This is the world of Edwin Abbott's classic tale, Flatland. The beings who live there, squares, triangles, circles, can move left and right, forward and backward, but they have no concept of up or down. Their entire reality is a flat plane. Now, imagine a three-dimensional object like an apple passing through their two-dimensional world. What would the Flatlanders see? They wouldn't perceive the apple in its full, rounded glory. Instead, they would witness a series of mysterious, changing shapes. As the apple first touches their plane, they'd see a single point that suddenly grows into a small circle. That circle would expand to a maximum width as the apple's equator passed through, and then it would slowly shrink back to a point before vanishing entirely. To a Flatlander, this would be a baffling and miraculous event, a shape that appears from nowhere, changes size, and then disappears. They could measure the circumference of the circle at every moment, but they could never comprehend the true, three-dimensional nature of the object causing it. They are trapped by the limitations of their perception. Now, take a moment and turn that perspective around. We are the Flatlanders. Our senses are exquisitely tuned to perceive three dimensions of space, but we are, by our very biology, blind to any others. If a four-dimensional object were to pass through our three-dimensional world, the experience would be just as bewildering for us as the apple was for the square. A hyper-object or a being from a higher dimension would not suddenly pop into our view in its complete form. Instead, we would witness a three-dimensional cross-section of it. It might appear as a shimmering, impossibly complex shape that seems to morph and change its properties in ways that defy our understanding of physics, its volume fluctuating without any apparent cause. It could seemingly manipulate our reality from the inside, reaching into a sealed safe to remove its contents without ever opening the door, or seeing every room in your house simultaneously from a perspective we cannot even visualize. To such a higher dimensional entity, our entire universe might appear enclosed and flat, much like a page in a book, and they could potentially interact with any part of it without moving through the space in between as we must. This isn't about magic, it's about geometry that exists beyond the reach of our senses, and it forces a profound humility about the limits of our own perception. So where are these extra dimensions if we can't see them? String theory suggests they are not expansive, empty voids like the three we know. Instead, they are curled up or compactified into an astonishingly tiny, complex shape at every single point in space. The most common analogy is to look at a long, thin garden hose. From a distance, it appears to be a simple one-dimensional line, but if you were an ant crawling on its surface, you would discover a second dimension, the circular path around its circumference. The extra dimensions of string theory are thought to be like that circular path, but folded into intricate, multi-dimensional shapes known as Calabi-Yau manifolds. These are not shapes we can easily picture. They are six-dimensional mathematical objects of breathtaking complexity. Their geometry isn't just a curiosity, it is absolutely critical. The specific way these dimensions are folded determines the fundamental laws of physics in that universe. The shape dictates the number of particle families, the masses of electrons and quarks, and the strength of gravity and the other forces. A tiny change in the geometry of this hidden dimensional landscape would result in a universe with completely different physics, one that might be utterly sterile and incapable of supporting any complexity at all. This is how the higher dimensional framework of string theory naturally gives rise to the vast landscape of possible universes, each with its own unique physical signature. This incredible journey from the quantum weirdness of strings to the hidden geometry of extra dimensions represents humanity's most ambitious attempt to solve the greatest puzzle in all of science, the quest for a theory of everything. For over a century, physics has been divided into two spectacularly successful but fundamentally incompatible kingdoms. On one side reigns quantum mechanics, which describes with incredible precision the behavior of the very small, the particles and forces that build atoms and molecules. On the other side stands Einstein's general relativity, which masterfully describes the force of gravity and the nature of the very large planets, stars, galaxies, and the cosmos itself. The problem is that these two theories speak different mathematical languages and break down when forced to describe each other's domains. At the center of a black hole or the moment of the Big Bang, where gravity is immense and volumes are tiny, our current physics simply stops working. A theory of everything is the dream of a single, elegant framework that seamlessly unites quantum mechanics with general relativity, a set of equations that can describe the force of gravity with the same quantum rules that govern the other three fundamental forces. String theory, with its vibrations in higher dimensional space, is a prime candidate because it naturally includes a particle that has the properties of the hypothetical graviton, the quantum carrier of gravity. It doesn't add gravity to the quantum world, it shows how gravity emerges from it. Ultimately, all these mind-expanding ideas, the quantum multiverse, the inflationary bubble universes, the holographic principle, and the higher dimensional landscapes of string theory are not competing visions. They are different pieces of the same grand puzzle, converging from various angles on a single, breathtaking conclusion that our reality is far more vast, strange, and interconnected than we ever dared to imagine. The search for a theory of everything is more than a technical challenge. It is the highest expression of human curiosity, a quest to understand not just our universe, but all possible universes, and to find our unique place within that infinite tapestry. It weaves together the fabric of space-time, the music of vibrating strings, and the quantum information of holographic boundaries into a potential master narrative of existence itself, a story we are only just beginning to read. For over a century, the world of physics has been a house divided, a kingdom split into two spectacularly successful but stubbornly separate realms. In one corner, we have quantum mechanics, the rulebook for the impossibly small. It governs the bizarre and probabilistic dance of particles and forces that build atoms, molecules, and everything we see. Its predictions are stunningly precise, tested to more decimal places than any other theory in human history. And in the other corner, we have Einstein's masterpiece, general relativity, which describes the force of gravity as the curvature of space-time itself. It masterfully explains the motion of planets, the bending of light around galaxies, and the evolution of the entire cosmos. Both of these theories are monumental achievements, yet they speak entirely different mathematical languages and fundamentally break down when forced to describe each other's domain. At the center of a black hole, where gravity is immense and space is tiny, or at the very moment of the Big Bang, our equations simply blow up into meaningless infinities. This great schism is the most deep-seated problem in all of physics, and the dream of healing it, of finding a single, elegant set of equations that can describe all forces and all particles under one roof, is the legendary pursuit of a theory of everything. This isn't just an academic exercise to tidy up the textbooks. A theory of everything would be the ultimate key to unlocking the deepest secrets of existence. It would allow us to peer back to the very first moment of time, to understand the true nature of singularities, and to answer the question of why our universe has the specific set of laws and constants that it does. And as we've journeyed through these ideas, a startling possibility has emerged. The path to this grand unification might not lead to a single, unique universe, but directly through the heart of the multiverse. The very features required to stitch quantum mechanics and general relativity together, whether it's the extra dimensions of string theory or the granular structure of spacetime in loop quantum gravity, seem to naturally generate a landscape of possibilities, a vast ensemble of potential realities. It's as if the cosmos is telling us that to finally understand the one universe we see, we must first comprehend the infinite ones we cannot. The leading contender in this quest for decades has been string theory, which we've touched on before. Its core idea is breathtakingly simple. Replace the point-like particles of traditional physics with unimaginably tiny, vibrating loops of energy. The different ways these strings vibrate give rise to the different particles we observe. One vibration pattern is an electron, another is a photon, and crucially, one pattern has the exact properties of the graviton, the hypothetical quantum particle that would carry the force of gravity. In one elegant stroke, string theory doesn't just add gravity to the quantum world, it shows how gravity emerges from it. But for this beautiful mathematical symphony to work, it requires more than the 3 dimensions of space and one of time we're familiar with. The equations only make sense in 10 or 11 dimensions. This necessity forces the theory to propose a vast landscape of possible solutions, a dizzying array of ways those extra dimensions can be curled up into tiny, complex shapes. And each different shape results in a different set of physical laws for its universe. String theory, in its quest to be a theory of everything, doesn't predict one universe. It predicts a multiverse of virtually limitless possibilities, with our own cosmos being just one particularly fortunate entry in an infinite cosmic catalog. But string theory is not the only path up the mountain. Another compelling approach, known as loop quantum gravity, takes a very different tack. Instead of adding extra dimensions, it focuses on reimagining the very fabric of spacetime itself. It proposes that space is not smooth and continuous as Einstein described, but is actually woven from a network of tiny, discrete, one-dimensional loops, a kind of spacetime fabric made of individual threads. This quantum of space is inconceivably small at the Planck scale, but this granularity prevents the formation of the gravitational singularities that break classical physics. In this model, the Big Bang wasn't a singularity but a big bounce, a moment where a previous universe collapsed and then rebounded into our own. And just like string theory, this framework also naturally accommodates a multiverse. The quantum fluctuations that govern the evolution of this granular spacetime could lead to the spontaneous birth of new universes from the foam of the old, creating a forever renewing cosmic ecosystem where multiple realities are constantly budding off from one another. It's a profoundly different vision from string theory's landscape, but it arrives at the same stunning conclusion. Our universe is likely not alone. This pursuit, whether through the vibrating strings or the woven loops of space, represents humanity's highest intellectual ambition. It is a quest that weaves together the hardest of sciences with the deepest of philosophies, all fueled by a sense of wonder that has driven us since we first looked up at the stars. We are trying to build a single narrative that can encompass everything from the frantic dance of quantum particles to the majestic whirl of galaxies, and in doing so, we are forced to confront the ultimate nature of reality itself. The fact that this journey seems to point toward a multiverse is not a complication or a distraction. It is perhaps the most important clue we have. It suggests that the universe is not just stranger than we imagine, but that it must be, by its very fundamental structure, stranger than we can imagine. Our search for a single, simple theory of everything is revealing an everything that is gloriously, infinitely complex. We've traveled an incredible distance together, from the ghostly realm of quantum possibilities where particles exist in multiple states at once, to the breathtaking cosmic inflation that may be spawning countless bubble universes beyond our sight. We've seen how ancient philosophers and modern scientists, using vastly different tools, have arrived at the same humbling conclusion, that our reality is likely just one thread in an infinite tapestry. This journey does more than just fill us with wonder. It fundamentally reshapes our perspective on everything. It installs in us a profound sense of cosmic humility, a quiet acknowledgement that no matter how much we learn, our knowledge will always be partial, a single flicker of light in a vast and shadowy expanse. This isn't a cause for despair, but for liberation. It frees us from the arrogance of certainty and opens our minds to a lifetime of learning, questioning, and exploring. In a world that often feels increasingly polarized, where people cling fiercely to single, rigid viewpoints, the multiverse concept is a powerful antidote. It trains us to hold multiple possibilities in our minds at once, to be comfortable with not knowing, and to approach the unknown not with fear, but with a generous and open curiosity. This new cosmic perspective is far more than an intellectual exercise. It's a practical toolkit for navigating the complexities and uncertainties of our daily lives. When faced with a difficult decision, instead of agonizing over the one right path, we can learn to appreciate that every choice opens a door to a new adventure, and that other versions of us are faithfully exploring all the roads we did not take. This can dissolve the heavy weight of regret and replace it with a light-hearted sense of exploration. It encourages us to take thoughtful risks, to be more empathetic toward others whose paths have diverged from our own, and to see our own story as a unique and valuable chapter in a much grander narrative. By fully embracing this universe of possibilities, we inject our lives with a renewed sense of awe and purpose. We begin to see the world not as a static stage, but as a dynamic, ever-unfolding story in which we are both the authors and the characters, endowed with the incredible power to shape our individual experience within this one precious reality. This journey through the multiverse ultimately brings us back to ourselves, to this moment, and to the profound responsibility and joy of making it count. We've explored the exhilarating idea that our reality is just one of countless others, each with its own laws, histories, and possibilities. From the quantum roots of the many worlds interpretation to the cosmic implications of eternal inflation, from the ethical dimensions of infinite choice to the technological frontiers that may one day let us touch these concepts, this journey reveals a cosmos far grander, more mysterious, and more interconnected than we often assume from our limited vantage point. It challenges not just what we know, but how we know it, inviting us to see existence itself as a vast, dynamic tapestry where every thread is a world, every color a different set of physical laws, and every pattern a story waiting to be told. This perspective does more than expand our map of the universe. It redefines our place within it. We are not insignificant observers on a lonely rock, but conscious participants in an unfolding drama of infinite scope. Every question we ask, every theory we test, and every dream we entertain is a step toward engaging with that grandeur. Remember that questioning and imagining are not idle pastimes, they are the very engines of discovery, the tools that have brought us from cave fires to quantum computers and will carry us forward into understandings we can barely glimpse today. So I encourage you to carry this sense of wonder with you. Keep looking up at the night sky not just as a canopy of stars, but as a window into one reality among many. Stay curious not just about what is, but about what could be. Share your thoughts and questions in the comments below. This conversation is just beginning, and every perspective adds depth to our collective exploration. If this journey into the fabric of reality sparked your imagination, consider subscribing for more deep dives into the mysteries of space, time, and existence. Thank you for joining me in peering into a universe of possibilities, a journey where every question leads to new horizons, and every answer reveals how much